Hello everyone, good morning. On behalf of Thapar Amateur Astronomers Society, I welcome you all. I hope that all of you are in the best of your health. We'll be starting off in a few more minutes, and I request all of you to wait patiently. Thank you.
सर तुमचा ऑडिओ बंद आहे.
Okay, we have all our three teachers with us. I welcome you all from our behalf. Parakaram, you all can start with the presentation.
Astronomy compels the soul to look upwards and leads us from this world to another. With these wise words of Plato, I would like to welcome everyone to TAS GMRT-Rad at Home workshop. I, MBBS Manoj Kumar, along with Parakram Singh Tanwar and Muskan Chojar, will be your hosts for the event. A little bit about us. We at Thapar Amateur Astronomers Society look to cultivate scientific temperament and nourish inquisitive young minds to encourage innovation in young aspiring minds who do not get a chance in their daily load of engineering. With our events like Eureka, our flagship event, a lecture symposium in which lecturers from all over India come together and deliberate on one particular topic. Second event is our Akash Ganga. This is a series of workshops which is organized for school children of Patiala to spark curiosity in their minds and inspire them to become great astronomers. GDs, we hold regular group discussions to share a love for astronomy, but due to the pandemic, we are not able to do so. Instead, we host Cosmos watch parties in which we hold DDs after the Cosmos episode and discuss whatever happened in that episode. We also hold quizzes which increase our knowledge base, but also test, but is also an invitation for others to test their knowledge. Next is a Cosmic Cafe podcast. This is one of our new projects and is a podcast on YouTube channel in which we discuss about topics we are passionate about like time travel, grandfather's paradox, or black holes. Now, coming to our co-host, that is Rad at Home. Rad at Home Astronomical Laboratory is the first Indian citizen science research astronomy platform in astronomy. This zero-funded, zero-infrastructure nationwide Inter-University Collaboratory has been established as a platform wherein any BE, BSc, undergraduate, graduate can do multi-wavelength in extragalactic astronomy research using ABCD research. ABCD research stands for any BSc BE can do research using GMRT settings at home, anywhere in India by joining Rad at Home Collaboratory for free. The collaboratory has a novel approach of training citizens to get them ready for research. Through 1 week Rad at Home discovery camps, suitable candidates are trained via one-on-one interaction with professional astronomers. Coming to the general guidelines of the event, participants are required to join with their full name. They are requested to join with the registered email ID. Participants will get certificates based on their attendance and performance. Misbehavior will not be tolerated and participants will be immediately removed from the meeting. All participants will be muted while the lectures are going on. Any questions or doubts can be returned in the chat box to the co-host named moderator. I would like to invite Parakram to invite the guests.
Okay, so now I'd like to take this opportunity to introduce our guest lecturers for today. First up, we have Dr. Mamta Gulati. She is our Vice President of TAS, and an Assistant Professor at Thapar Institute of Engineering and Technology. Next up, we have Dr. Chiranjeev Konar, who is an Assistant Professor at Amity Institute of Applied Sciences. And finally, we have Dr. Ananda Hota, who is a UGC faculty at UMDAE CEBS in Mumbai. Welcome, lecturers. Now on to the schedule. Our first section for today is our lectures. The first lecture will be on multi-wavelength views of galaxies by Dr. Mamta Gulati. The second lecture will be on supermassive black holes and active galactic nuclei by Dr. Chiranjeev Konar. And final lecture will be on black hole galaxy co-evolution study with GMRT and RAD at home by Dr. Ananda Hota. These lectures are expected to take half an hour each, and we aim to wrap them up by 12 p.m. Next, we'll have the daily Galaxy RGBC section. It is an interactive session with the registered participants. There will be a demonstration on how to make RGB and contour images by Dr. Ananda Hota and the RAD team. This event will wrap up by 1 p.m. Then we'll have a 1 hour lunch break from 1 p.m. to 2 p.m. After which there will be a discussion on RGB contour images posted by the participants. This will wrap up by 3:30 p.m. Finally, we'll have an event, Dil Se Discovery, in which a selected group of participants will be assigned mentorship by an e-astronomer or a trained citizen scientist. This event will take 2 hours from 3:30 p.m. to 5:30 p.m. Now on to the first lecture on multi-wavelength views of galaxies by Dr. Mamta Gulati. She is the Vice President of TAS and an Assistant Professor at Thapar Institute of Engineering and Technology. She has a specialization in astronomy and astrophysics along with gravitational dynamics. Now I'd request ma'am to present her lecture and take over the stage. Thank you.
Yeah, good morning, everyone. Thanks, Parakram, for the introduction. I welcome everybody on behalf of TAS on board for the lecture series and the workshop. Can you just let me know if I'm audible? My voice is okay?
Yes, ma'am, you are perfectly audible.
Yeah, thank you. Okay, so I'll start with my presentation. Just give me a moment. I'll share my screen.
Sure.
Okay, so that's the first slide of my presentation. So I'll basically talk about multi-wavelength view of galaxies. And so I expect to take around 30 minutes to do my presentation. So I'll most likely be concentrating on one or two observational properties. And then from there, we will try to go on that how do we connect it to theory, in the sense that given the observation, how do we actually try to map the observations, or how do we actually use those observations to get to a theoretical model, or to get to the physics of how these observations, or how these structures, or how these say for example the orbits of stars and galaxies are formed. So let me just take you through a brief introduction of mass, length scale, and time scales in astronomy. So mass is, in astronomy, we mostly measure mass in solar masses. So that's one solar mass is around 1.99 into 10 to the power 30 kgs. To get a useful number, we just make it rounded off to 2. If you're just making an order of magnitude estimation. Then we have that masses of stars lie between 0.1 solar mass, 20 solar mass range. And a typical galaxy like Milky Way has a mass range of around 10 to the power 11 solar masses. Then we have the unit of length, which is astronomical unit, which essentially is around 1.5 into 10 to the power 11 meters. And 1 parsec is another unit of length, which is around 3.09 into 10 to the power 16 meters. So 1 astronomical unit is the distance between Earth and Sun, and 1 parsec is the distance to the star if the parallax to the star is 1 arc second. So these are two numbers which are coming from observations, or which have a physical significance. They're not just numbers that are there. Then we have standard unit of measurement of lengths in galaxies is, say, for example, kiloparsec. For a cluster of galaxies, the length scales that we have are of the range of megaparsec, and the size of the universe is of around gigaparsec. So kilo is 10 to the power 3 parsec, mega is 10 to the power 6, and giga is 10 to the power 9 parsecs. Then we have time scales. So in case of time scales, we have a variation in time scale from millisecond to giga years. As far as the time scales in astronomical objects are concerned, for millisecond, we have in millisecond range, we have pulsars whose time period is of the order, whose rotation time period is of the order of millisecond. And for giga years, that's approximately the age of the universe that we have. This is a schematic of galaxy or our solar system to start with. So on the left, we have a schematic picture of our planet. Then that planet is further a part of solar system. It's a schematic, so not all the planets are shown over here. Center is the sun, and then you have almost elliptical orbits, almost circular orbits for the planets drawn. We are here somewhere, and then if you zoom on inside in the galaxy, we have this tiny dot in one of the spiral arm at approximately a distance of 8 kiloparsec from the center. And that's a view of our own galaxy. And then if we jump on to the right-hand side image, this is a Hubble Space Telescope deep image of one snapshot of the deep images that the HST takes. And there are thousands and thousands of galaxies in this image. Each of the dot over here in the image represents one galaxy. So there's a famous dialogue by an astronomer who says that we are just stardust. So essentially, we are a very, very, very tiny part of the whole universe as you look at it. So coming back to the galaxies, what are galaxies? So galaxy is a huge collection of gas, dust, and billions of stars and their solar systems, so which are gravitationally bound by their own self-gravity of their components. And galaxies essentially also, most of the galaxies also support a supermassive black hole at their centers. And our own galaxy is called Milky Way. And coming to one of the pictures of Milky Way, this is a picture taken by a normal naked eye. You can see it from naked eye. It's somewhere near Chile. And if the sky is dark, you can see a patch of this dark patch of bright light and some dark lines going like this in the sky. And this essentially is one of the spiral arms of our galaxy, or the disk plane of our galaxy Milky Way. I have had the opportunity of also seeing this kind of small dark patch from an observatory in Kavarlur. So it looks spectacular. So you have to be away from the city lights to actually see it. There are many galaxies besides our own galaxy. This is not an unknown fact for us by now. And there are almost millions of galaxies in our universe. The number counting is still going on, and we are discovering new and new objects every day. Then we have the classification of galaxies based upon their shapes and sizes. So broadly speaking, they are categorized into three categories. One is spiral, which are basically disk galaxies, very thin disk galaxies. And you can see some spiral patterns like this in the galaxy. And by the end of the discussion today, I'll try to explain then how these spirals are formed, going from observations to the theory. Then you have elliptical galaxies. They are elliptical, means they are three-dimensional ellipsoids. And then there are irregular galaxies, which do not have a regular shape. And we'll also see that how these are expected to form. Then you have the classification again. So not just their shapes, they also distinguish with each other based on the content they have. So for example, elliptical galaxies have less gas. They have relatively older or more evolved stars present. And then they are orbiting around the common center of galaxies. And each of the stars, they are not in a very described motion around the center. Rather, there is a random motion dominating the motion of the stars in the galaxies. All these properties that I've told over here were discovered after this classification was given earlier of by just their shapes. So this classification of shape also led to uh, uh, this distinction when also was supported by this distinction when it came to the measurement of the content of each of them, and that further supported their formation theories. So in case of spirals, you have young stars present. There's along with the central bulge of old stars are there. We'll just see a few pictures of galaxies in which we can see these bulge and young stars in the galaxies. Then you have stars orbit in case of spiral galaxies in almost circular orbit around their centers. So their formation, how they are formed and how they are evolving, also can be seen from what kind of orbits the star actually is following in the galaxy. So we'll also see some kind of orbits in the galaxies, and we'll try to explain how those orbits are formed by the end of today's session. So these are the two main questions that I'll try to answer by the end. And so coming to the classification again, this is the Hubble, same classification represented as Hubble tuning fork diagram. So you have ellipticals going in one single row like this. Number with the elliptical represents the eccentricity of the ellipsoid that we have. Then the branch of spirals is bifurcated into two depending upon the presence of a bar, a straight bar kind of structure at the center. So our own galaxy, Milky Way, is a barred galaxy, and it's basically an SBC type of galaxy. In spirals, ABC would mean that how tightly wound your spirals are. If they are more tightly wound, you are at the smaller alphabet, that is A. If they are loosely wound, you are at a higher alphabet ABC in your sequence ABCD. Lenticulars are the intermediate forms. They are neither ellipticals nor spirals, and they have a central bulge, extended disk structure, but they do not show any spiral structures. These are lenticulars for the information. Now, this looks very clean and nice tuning fork diagram, but coming to the present or situation, this is the image from the Spitzer telescope, and in the near infrared galaxy survey. And now we are in the zoo of galaxies, where you see a lot of overlap between the different distinctions and stuff like that. And these are irregular shown over here, which could not be distinguished in any of these shapes that we saw over here. And so this classification, since is based on what you see, and you have to do it by eye, which side of the tuning fork diagram we go. So it's a very tough job right now with all the data that is available for the galaxy imaging and stuff like that. So there are people who are trying to move to deep learning and machine learning actually to distinguish these galaxies based upon whatever input we can give from hand. So it's a kind of supervised deep learning that they're trying to use for analysis of this large data sets that we have. That is for this finding the distinction between the shapes of the galaxies and then categorizing them into the classification of either elliptical, spirals, or irregulars, and so on. So this is a schematic of Milky Way that we have. Milky Way extends up to, our own galaxy extends up to 30 kiloparsec in diameter. You have a bar at the center. Then you have a bulge that is something like this in the center, and bulge contains essentially old stars. The disk portion contains essentially new stars. So that also gives us an idea about how these would have formed. Since the bulge is having old stars, it is expected that the bulge formed first, and the disk is relatively younger than the bulge. This is the side view of the galaxy. So above and below the plane of the disk galaxy, we see globular clusters all spread almost symmetrically about the galaxy plane. I mean, this is schematic. We can see the symmetrical distribution all the way up to end, but however, it's more dense towards the bulge area. Then we also have a dark matter halo surrounding it, and this is the position of the sun. As far as the position, our own position is concerned, in the galactic view, it coincides with the position of the sun itself. And now coming to the images of other galaxies. So the galaxies essentially can distinguish with each other's the spiral galaxies. I'll first give a few images of spiral galaxies. Can be distinguished from the are distinguished essentially by the way the spiral arms are actually present in the galaxies. So you have a few galaxies which have a very good grand design spirals. These are called. So you see very clearly. You see two spiral arms going like this. Let me just point that out over in the image. So if you see this image, it has a very clear two-armed spiral going like this. One is this and the other one is this, rising from a very symmetrical, rising in a very symmetrical manner from the center. Similarly, this one is M100 and this galaxy is M51. So in this case also you see a very nice two-armed spiral coming out symmetrically from the center and winding up like this. This bright object on this right of this galaxy M51, this is also called Whirlpool galaxy. So this is essentially a satellite galaxy. For the satellite means there are small galaxies surrounding a big galaxy, which is almost merging into the M51 galaxy right away. And we'll come to this image later on in our discussion. Then there are intermediate scale spirals, which are not as grand as two-armed spirals that we just now saw. But in this case, they arise symmetrically from the center as we had earlier, but they are not very grand design. Like if you follow this one, the earlier one, like this, you'll see that there are other branches also coming out of the galaxies that we have. Similarly, in this case, you can see an arm starting from here going like this, but you also can see an arm coming out like this. And similarly from here, there's an arm like this, and then you can see a little distortion from here. So these are intermediate scale spirals in which you see a grand design kind of structure, but you also see some small arms here and there. And then we come to other galaxies, like this one is a flocculent spiral. Flocculent structure, we mean that you do not have a clear distinction in the spiral arm like this, but you can trace these arms and you have small structures coming out of the arm like this. So these are called flocculent spirals, and this is M63. And then this is a barred spiral galaxy in which you see a very prominent bar at the center. This is the bulge portion, and these are very nicely two-armed spirals coming out of the end of the bar. Our own galaxy resembles something like this as we see, but right now there's our own galaxy right now, as far as the modeling goes, it's a four-armed spiral, not this very clearly two-armed spiral coming from the end. The main two arms of the spiral, our own spiral galaxy, starts from the end of the bar. However, it's almost decided that we do have four-armed spiral structures present in Milky Way. And there's another group also which says that you also have a fifth arm based upon the magnetic field in the Milky Way. So you kind of see 5 flipping of magnetic field sign. From there, they have also an model which says that we might be missing something in the galaxy picture. So this is the coming back the image of M51 again, the Whirlpool in different wavebands now. And I might also suggested that we also talk about multi-wavelength view of the galaxies. So we'll see the grand arm spirals, and we'll also see these as we'll see the traces of spiral arm in different components of the galaxy. By different components, we mean that stars, we have gas, we have old stars, we have new stars, relatively, and we also have different Yeah, I'm sorry. I think I got disconnected. I'll just share the screen again. Okay. So I was at this slide where I was discussing the different multi-wavelength view of the Whirlpool galaxy. We just now saw this image earlier, which is an optical image that we have. And these are other images. The first one, these are the images of galaxy different wavelengths. So the first one that we have is the radio image. The radio portion traces the gas arms in the spiral galaxy. And then we have essentially the this one is an infrared image which coincides with the mass arms.
Is the slide shared by others participants? I can't see. Now it has come.
Okay. Yeah, sorry for that. There was some internet issue. My internet got disconnected.
Yeah.
So it's visible right now, right?
Right now it is okay.
So, okay, thank you. So this near infrared image actually coincides with the mass arm. By mass arm, we mean that you have maximum mass present over here. And this is basically giving us the fact that most of the stellar content of the galaxy lies in these arms. Then you have gas arms in first image, which coincides with the maximum gas density. Then you have bright stellar arms of the luminosity density of young stars, which can be seen in the third image, which is in the optical. This is the ultraviolet image, and the last one is the X-ray image. X-ray image essentially gives us the high hot gas density, and the ultraviolet images actually gives us the basically the hot stars present in the galaxy. So this is different view, and if you see very carefully, and let me just go back to the previous image that I have shown, that's zoomed version of these images. If you see from here, and I try to see from here very closely. Let's watch this portion of the spiral arm. So you see some red spots at the bright arms coming like this. Then you have a dark lane in between, and then we have a bright portion again. So these three kind of portions in the spiral arm actually gives us the different components. Dust lane, dark portion is the dust lane in the galaxies. Red spots are essentially the star formation clumps, the gas clumps, which star formation where there are massive star formation happening in the galaxies. The white bright lights actually, or the blue light traces the young star population. So this kind of gives us that your spiral arms are evolving as you go. Okay, so you have gas contractions. Dust arms also has a lot of contractions in the gas clouds happening there. Then the star starts forming. By the time the star starts forming, your spiral arms moves ahead. So it's an evolving. The spiral arm is not a stationary structure, you can see from here, whereas it's an evolving structure. I'll come to a schematic later on, which will make this deduction from these 3-4 kind of different arms that we see in multi-wavelength images also very clear. So there are other traces of spiral arms also can be seen, like the dust arms. They are displaced inside the bright spiral arms. Then you have relativistic electrons. They trace the magnetic fields. Then you have molecular gas, which traces the high density gas in the spiral arms. Then we have neutral hydrogen atom, which coincide with the brighter star arms and are also useful in mapping the velocities. And I'll come to this point also later on if the time permits, that it probes the dynamics of the spiral structures. Essentially, it gives the velocity or the orbits of your stellar structure. And then you have H, which also traces the bright spiral arms. Now, this image is the This image is the multi-wavelength image of our own galaxy, Milky Way. The top panel that we have is a radio continuum. Next, you have atomic hydrogen. You can clearly see that the radio continuum has a quite bright bulge at the center. I mean, it's extended away from the disk also in the center, whereas the atomic hydrogen, you can see that they are quite confined within the disk. This is the molecular hydrogen. You see that molecular hydrogen is missing, almost missing as far as from the disk plane. This is the infrared image, which coincides with the these two. The fourth and the fifth one are in infrared and near infrared, which gives us the stellar density. Then you have optical images, optical portion. This is the X-ray, which and the gamma rays, which gives you the hot gas in the disk. Hot gas, as you see, there is a dark patch in this portion in the disk plane, whereas you see much of the hot gas above and below the disk plane. And as in gamma ray, you see a quite good distribution as far as in the disk plane. So these different kind of components also give us some idea about how the galaxies are also evolving. So then you have, then I'll come to a different topic rather than looking at galaxy as a whole. Let's just look at the orbits of the star, and we have a video. Is the video visible now?
Yes, ma'am.
So these are the stellar orbits as we zoom into the center. This is a schematic video that is being made. And as it is zooming in the center, all these are stars. This is 1 light year from the center. And then you go on zooming within the center of the galaxy and you start seeing orbits. So each of these elliptical lines actually is a star orbiting around the center. And we keep on zooming as we go ahead. As we go in the center, you do not have your orbits in the plane because we have a bulge at the center, and these are three-dimensional orbits. This yellow line over here, this radius over here is 1 light month for us. And as I zoom further and further and further, we get to 1 light day now. And now you are able to see the orbits, the stars moving in their orbits very clearly, very slowly. This is simulated video though, but we do have observations of these stars near the very center of the galaxy. And now we have almost zoomed to 1 light day in the image. 1 light day means the time taken by the light to travel. I mean the distance traveled by light in 1 day. That's 1 light day. And yeah, so if you see, these are all the orbits. And coming to the observation now, this is the observed image that you have at the center of the galaxy. So this is an observation of almost around 18 years of the galactic center, measuring the orbits. So measuring these orbits, a part of this orbit gave them the eccentricity and the orbital parameters, which also gives an idea about the mass of the central object of the galaxy, coming from simple, I mean, a rough estimate can be calculated from simple Newtonian dynamics. However, this exact calculation is not simple Newtonian dynamics coming there. These are stars. You see that these stars are elliptical orbits, and some of them are also tilted elliptical orbits. Now we'll see one more image of the orbit of the sun. This is an image of the sun taken, there's a camera image of the sun taken from one location for the whole year. This you can see very clearly, an 8 structure is made over here in the image. And if you want to see this image, I've simply taken from APOD, which is the astronomical picture of the day site. Then you have this as your image of 1 month, that is 27.3 days of the moon, taken from one particular location in the earth. And then you have an image of the sun taken from the for the whole period from the Mars, which also shows us the orbit of sun as seen from the planet. So this is from the Earth and this is from the Mars. You can see that this lower loop of 8 is also seen as you see from the Mars orbit. In sun also, for this moon also, we also see an elliptical orbit like, an 8 or infinity structure like this. I'll come to a very small explanation of this as we go. Now coming to the target questions, I'll give very brief theoretical model for these two target questions. That is how the spiral arms are formed, spiral galaxies are formed, and how the observed orbits are formed. So the first one, I'll skip this definition part. These are just the definitions for how do you characterize your spiral arms. That is the number of spiral arms are there, whether the arms are relay, that gives me the direction of pointing of the arms. Then you have pitch angles, then you have pattern speed of the spiral patterns that are available in the galaxies. So these are always observed quantities as you see from the images, and they kind of also give us an idea about what kind of how these galaxies were formed. That was one of the most challenging question from the astronomers. The first galaxies appeared almost around as little as 1 billion years after the Big Bang happened, which is probably 13 to 14 billion years ago from the present. Then you have two leading theories of the first galaxy formation. The first one says that the galaxies were born out of when the vast cloud of gas and dust collapsed under their own gravitational pull, and that allowed, since you had the density of the region exceeded the Jeans mass roughly, and the first stars were formed. And the other one says that, which has gained strength more recently, that rather than forming a huge big lump of one big lump of the size of the galaxy, there were small lumps of matter which were formed, and they kind of then collapsed into each other to give the universe, the present formation for present galaxies structures that we see. So according to this theory, the most earlier galaxies that were formed were spirals, and then the spirals would have much to form to the one which is much more the evidences that we have is that the spiral galaxies are present. The population of elliptical galaxies is more when you have dense environments. So that kind of supports the merger theory. That's just saying that our Milky Way also will be actually coinciding with our nearest galaxy, Andromeda, in near future. Near future, according to the astronomical numbers, is about 5 billion years. And now ellipticals are formed from spirals. Now the question is how the spiral galaxies are formed. The spiral galaxies formation is not a very simple process. They have a bulge at the center, then you have a disk, and then you have different mechanisms that then you have arms also present. Their ages are different, the components are different, so they should have been formed at different stages through different mechanisms. So the bulge mostly is composed of old stars, as we saw. So this indicates that the bulge of the galaxy would have formed probably in the beginning, and that is formed as I explained a little bit earlier, that you have a gas cloud that collapsed, and that is called a primordial collapse, and then you form stars there. And then from these stars, the disk on this central bulge region, the small gas clumps that were formed on the sides kind of collapsed and gave rise to a disk kind of structures of relatively younger stars. And this process happened after the primordial collapse has happened. So you see clearly see the distinction in the ages of the stars in the galaxy disk and the bulge. This is the now coming to how then the spiral arms are formed in the disk. The first explanation was that the spiral arms are just rigid rotation structure, as you can see in this video over here, that you have a spiral pattern rigidly rotating with this. If this is the situation, then this does not give any explanation to kind of different components at different position in the spiral arms as we saw in the observation. So this theory was ruled out from the observations. Then you had that rather than spiral arms being rigid structures, these are material arms and they kind of rotate, and the differential rotation of the galaxy gives rise to, these are just material perturbation, and the differential rotation gives rise to spiral structures. However, if this is true, this kind of winding will take place, and you should have a different, I mean, you should be able to see it in the observation. So the observation was such that they measured this pitch angle in the galaxy. Pitch angle is kind of gives how much winded your spiral arms are. So the observation of pitch angle for different galaxies did not supported this theory of winding the material arms like this. And then came the theory given by the by Brittle Lindblad, and he suggested that these are not fixed arms. However, these are wave patterns on the fabric. So just imagine it as something like a disk structure which is rotating about the center. There is material like this, and you have a wave pattern going on the material over here. And since this wave pattern, the compression and the rarefaction in the this is compression and the rarefaction in the mass of the disk. So you kind of, as the wave moves, it comes at a position, it increases the density, star formation happens there. And as by the time the star formation happen and we see the light from the star, the wave has moved further. So this gives us an explanation of why different components can in the spiral arms are seen at a different location. So this was recognized by Lindblad the first, and however, people did not believe in his theory until he died in 1965, and they were thinking that magnetic field is the reason for the formation of spiral arms. However, it was ruled on later on because magnetic field was not viable for giving the grand design spiral. The magnetic force that we have is not sufficient to hold a grand design spirals. It's a very simple order of magnitude calculation that can be done. So coming to the second question that I wanted to answer is the observation of stellar orbits. Do I have 2 minutes to finish this quickly?
Yeah, I'm sure. Yes, ma'am.
Okay. So I'll just go to the board over here and draw the orbits that can be there. So the Newton's theory of gravitation tells us that you will have elliptical orbits in the galaxy for any. So this is for any object, massive object over here. If you have a small mass object which is gravitationally attracted to it by just the Newton's force, it gives us that this will form an elliptical orbit with the massive object present at one of the focuses. So what we saw over there in the orbits diagram over here is the ellipse that we saw over here. Let me just go back to the slide of the image. Yeah, the ellipses that we are seeing over here are these ellipses, but however, these ellipses are not exact ellipses. There is a slight perturbation because of the other forces, because these two are not isolated objects. For example, there are other objects nearby. So there's a slight perturbation, and that perturbation is gives rise to an epicyclic orbits. That's what we term. So there is something called epicyclic orbits. In literature, you can find this term. What this says, theory is very simple. It just says that you have an elliptical orbit or nearly circular orbit, because the central object is considered much massive as compared to the object for which orbit we are calculating the orbit. So it's an near circular orbit, and on the top of it you have a small perturbation. So that small perturbation, if you look at from the frame, which is moving with this elliptical orbit over here. This perturbation over and above this elliptical orbit is an extra ellipse like this. So just to imagine this, you have a circular orbit like this, and then you have an ellipse. If you're moving with this circular orbit, the bigger circle one, you will see that the perturbation is an ellipse, and that is why this is called an epicyclic, or these are called epicyclic orbits. So the resultant structure will be an ellipse, something like this, and depending upon the dynamics, it might be a closed ellipse, an elongated closed ellipse, or an open ellipse, which gives rise to rosette kind of structures that you were seeing in the simulation earlier. So they will not be in closed orbit, and they will be moving like this in the disk plane, for example. So these are the examples. Coming to the 8 structure that you were seeing. So these are the 8 structures that you're seeing over here and here are this small ellipses you see in the epicyclic orbits over here, and the tilt of the plane. These are just ellipses in one plane, and the tilt in the plane is coming from the fact that our Earth is at an angle. The magnetic axis and the rotation axis of the Earth are at some angle. So that gives rise to this tilt, and the image appears to be an infinity image or an 8 structure. So this is all about the orbits. I mean, this was a rough explanation of the orbits that we see. And yeah, so I think I am almost done. The last thing that I wanted to discuss was rotation curves. I'll just briefly mention this. Rotation curves are the, for a disk galaxies, are basically the velocity curves. So you plot velocity versus the radius. The velocities are measured by 2 ways. One is that you measure the proper velocity, that is, you have a plane disk like this in the plane like this, and you measure the velocity, how the stars are moving like this. This observation is quite difficult. Then is, if you have this disk tilted at certain angle and you're seeing from here, what you will see is that the line of, say, for example, some gas present over here, carbon monoxide gas or molecular gas, the line profile of that gas will be red shifted or blue shifted depending upon whether this object is moving towards you or away from you, and that gives you the velocity of the matter. If you plot the velocity versus the radius, you'll see this kind of structure, this kind of velocity curves are present. I mean, most of the galaxies also see there is a flat rotation curve, that's what it is termed. And as far as the observations are, as far as the theoretical models are concerned, if we just see the observed mass, the visible mass, it should have followed this dotted curve going like this. So this extra velocity component told us that there is some extra mass present in the universe, and that gives rise to the that gives us the first evidence of the dark matter. This is the rotation curve from M33, which is taken from the Stefina.Deluca's paper. And I'll stop over here, and I hope you have taken something out of the presentation, that there are observations which gives, there are theories, and the bridging gap between them is that you match your observations with your theory, or you match your theory with your observation. So we as astronomers always tend to believe in what we see, and that's how we go about in discovering new objects and discovering new theories, finding new theories, and then giving a sense of physical processes that are happening. So I'll stop over here, and if there are a few questions, I'll be happy to take them.
Yeah, very good morning to ma'am and everyone present here, respected professors and participants. So, ma'am, the first question that we have received that we want to ask you is, in the galaxy rotational curve, why is it expected that the plot should have a positive slope initially before it drops? This question was asked.
So it's just simply coming from the fact that from the Newtonian formula of gravitational potential, that is GMM by R square. That's your Newtonian force, and that gives, if it is equated to just the centripetal force, mv square by r. Okay, so it's just saying that the velocity at any given radius will only be affected by the mass present inside, and this capital M is the mass present inside. So if you have an increasing mass initially, your velocity will keep on increasing, and that's just about it. Is that okay? So it's just saying that if your mass increases more than 1 by r, and that is what is observed, that the mass will increase. If this r just cancels, this small m just cancels, and you have v square is just gm by r, right? And if this mass, the increase in this mass is, it's the mass, and if you have a constant density rho, and then if this is a constant, then you have mass m by r cube. The dimensional analysis of this just gives me that this should be a constant, and then just this implies that mass goes as r cube, and putting it over here, this will just give me that velocity square goes as r square, right? The velocity should be linearly increasing. V should go as r, right? And that is why you see a linear increase in the beginning of this rotation curve. There's a linear increase going like this. Is that okay? Does that answer the question?
I guess it does, ma'am. I think the next question will be asked by Ishita.
Good morning, ma'am. So the next question was that, considering our age of the universe is very old, we should observe more elliptical galaxies as compared to spiral ones, as they should merge earlier, considering our age. Then why do we still observe gigantic spiral galaxies, which are 60% of overall galaxies we observe?
See, it's not that we are in that age old or at that age old structure that almost all the spirals have merged. We are not, the universe is not that old, first of all. And the second thing is that we do observe elliptical galaxies. The fraction of elliptical galaxies is more if you are in a dense environment, which favors the merger of galaxies. If you do not have a galaxy nearby, you will not have frequent mergers to happen, right? So if you have denser environment for galaxies, like in the, say, let me just go to one of the initial images that we had. This one. So if you have a denser region, you'll find more mergers happening there, and you'll find the fraction of elliptical galaxies is more over there as compared to the spirals. That's what I was saying. Is that okay, Ishita? Does that, I mean, or if whoever asked that question can just write a follow-up question if there is any.
Which I hope that's okay. So guys, we have a time constraint here, and we have to move on to the next lecture. So we had many questions. So the rest of the questions, I think you can mail to Mamta ma'am, and she'll answer them.
Yeah, I'll be very happy to answer those questions. This is my email ID. You can directly write to me, and I'll be happy to reply if anyone wants a further follow-up or any other question. So I'll just stop this share, and thanks for being a very good audience. I hope you had a fruitful output out of the discussion that I had today. So bye for now. And on my behalf and from the society, I would like to welcome. I would also like to extend a welcome to both our speakers, both our other speakers for the day, and Dr. Charanjeev and Dr. Ananda. And I would like to thank them for being very supportive in organizing this workshop, from being from TAS and from my side. So welcome aboard Dr. Ananda and Dr. Charanjeev. Thanks for being here.
Thank you very much.
Yeah. So over to you guys, over to the moderators for the next presentation.
Thank you, ma'am, for this amazing lecture.
Thank you, ma'am.
Yeah, welcome.
So now I would like to invite Muskan. Muskan, are you here?
Yeah, I'm here. Am I audible? Yeah. Thank you, Dr. Mamta, for this amazing lecture on the various types of galaxies. Now, we have another interesting lecture planned for you on supermassive black holes and active galactic nuclei by Dr. Chiranjeev Koner. Dr. Koner is an assistant professor at Amity Institute of Applied Sciences with specialization in astronomy and astrophysics. With a plethora of notable international publications, Dr. Koner is now present here to enlighten us. We welcome you, sir.
Hello. Can you hear me?
Yes, sir, you're
Yes.
audible.
Okay. Okay, thanks, Muskan, for kind introduction. It's my pleasure to be invited by this initiative. And today I'll be presenting something about what is called active galactic nuclei. Let me share the screen. Can you see my screen?
Yes, sir.
Yes.
Yes, sir.
Okay. I think some background sound is coming. Can all the participants mute yourself?
Chiranjeev, sorry. Hello, Chiranjeev. Sorry for the interruption. You're muted. Can you just unmute yourself?
Sorry, it is happening automatically.
Okay. No, yeah, it's audible.
So can you hear me now loudly?
Yeah, loud and clear.
Okay. So I'll be talking about what is called active galactic nuclei. And essentially it is a supermassive black hole system, but this is hosted by galaxies. And in the morning, Mamta has given a beautiful talk on what galaxies are and their classifications. So therefore, it has made my job very simple because I will go through those slides very quickly. So this has been already explained by Mamta. See, this is the galaxy classification scheme, which was introduced by Edwin Hubble in 1926. And you can see that elliptical galaxies are at the base of this tuning fork, and the two arms we have placed.
The slides are not changing. Chiranjeev.
You can't see my slide, this tuning fork diagram?
No, I can't see at least. Organizers, can you confirm?
Can you see the tuning?
Chiranjeev, it's still on the first slide.
Yeah.
Okay, so I don't know what I don't know what is happening.
Share and reshare. That's it happens sometime.
Yeah, I'll do that. I'll do that.
And the better would be that if you share your desktop and then be on this page.
Okay.
That is much smoother.
Can you see now?
It's still on the first slide.
Okay.
So you can stop the sharing first and then try it again.
Yeah, that will be good.
What kind of file you are sharing? PDF may be simple.
No, I'm sharing PPT.
That sometime of
Okay,
problems.
okay.
Yeah, it's working.
Okay. Now, is it working?
Yes.
Okay. I mean, there are so many things, what to click, and it got clicked somewhere else. It's problem.
Now go full screen.
Is this okay?
Yeah, we can see the 3D full diagram now.
Okay. So you can see in the arms of these tuning fork are the spiral galaxies, and here it is non-barred. There is no bar here. Here it is barred. So Mamta has already explained, so I'll not explain much about that. This is something about Edwin Hubble, and you can see that he is a very interesting character. He did his bachelor's in science, then master's in jurisprudence, which is basically law degree. Then he was teaching in a high school. Then he left that, then started doing PhD, and then he ultimately joined this Mount Wilson Observatory as a staff, and the rest is history, all. So the galaxy, when I talk about active galaxies, then I would like to show you some kind of pictures to show how this is different from normal galaxies. And structure-wise, it may not be much different. Here you don't see the arms, but there is a disk, underlying disk. Many of the active galaxies are basically disk galaxies, but not only this galaxy, there are galaxies which are elliptical galaxies, which is formed due to merger. And after that, what we see is that there is a central activity because of which a lot of light comes. And it is so much of light that if it is a disk galaxy, we don't even see the underlying disk so clearly. There are such galaxies where you don't even see. In the previous days, sensitivity was not that good. They could not even see the underlying disk at all. It looks like a round object, and people used to think it's a star, but later on they found that stellar spectra does not match with them. Therefore, they gave it a name quasi-stellar objects. So this needs to be explained, why so much of light coming, and they could not explain it by the starlight because stellar spectra does not match with this spectra. Therefore, this was the main problem for the astronomers to explain these things. So this is a normal galaxy I have shown. This is an active galaxy I have shown. And besides that, I will be classifying another thing which is called star-forming galaxy, which starburst galaxies, which are basically normal galaxy in terms of the activity in the central region, but they have a lot of star formations. So because of the spectral matching and how they are different, we need to know these three classifications. When you see them from a very distant, when you see the very distant galaxies, then you see just dot. You don't see such structure, right? Yet you can classify whether they are normal galaxy or active galaxy. And how do you do that? Classify these objects by knowing the spectrum. And I will go through some historical events through which it has come into, this kind of field has come into existence. That will give you a lot of interesting things in your mind, and you will be pondering over it. So I have decided to go through some amount of history about this subject. Generally, we know that the Seyfert galaxies, you might have heard about it. These are the active galactic nuclei, which was discovered in 1943. But before that, there has been some work, and Seyfert might have been motivated by his work, and he conducted his study. And it was none other than Pat E.A., who wrote a bulletin, Leak Observatory Bulletin in 1909, and there he specified his work in that observatory. He published work in his observatory, which is very interesting, which might have generated a lot of interest among the astronomers. And there it is saying that this investigation was undertaken to test the correctness of the statement frequently found in astronomical literature that the spectra of the spiral nebula are continuous. So you see that they are talking about spiral nebula, and still they used to call it spiral nebula, and it was not clear whether these kind of spiral nebula are extragalactic or it was within our galaxy. So people still didn't know that. And you see, the year is 1909. So in terms of physics history, if you think, you see, it was a time when still quantum mechanics was not discovered, and many of the physics was not discovered at that time. So we knew the spectral lines, but didn't know the origin of the spectral lines, etc. But still people observe lines, absorption and emission lines, and they are trying to figure out what this could be. And these are the sources: NGC 224, then 650, 651. These are the things he observed in his paper. In this bulletin, he observed an observation he reported. And then you can see that this is one. There are quite a few AGNs now we know, but now we call it AGN. But this was there, and it was a CIFAR-2 type. Now we know, but that time they got signature. There are 5 emission lines and 3 absorption lines found. Why this 5 emission line is important? Because it's very strong emission lines. Because if it is simple galaxy, that means it will be a collection of stars. In that case, if they observed some kind of collection of stars, they thought that this combined spectrum of all these collection of stars should be just like the stellar spectra, because it will be having a lot of absorption line, not the emission lines. Or if it is at that time they didn't know about the external galaxies. So if they knew, then they would have expected some emission lines also, because of there will be some kind of planetary nebula, and then H2 regions. They will also have emission lines, but they didn't have those pictures in their mind. So they were trying to explain why these emission lines are. So that gave rise to some kind of brainstorming discussion among the scientists. And he found these many emission lines. Now we know these 3 clearly recognizable. These are called O3 lines. This is doubly ionized oxygen gives rise to these lines. These we have to see from the chart what these lines are, and some absorption lines. Absorption lines would be to some extent there. That's because there are stars. Stars are characterized by absorption lines. And yes, and then even if you go back, then you can see that this particular galaxy 1068, so is basically an AGN, and from the historical records, I found. I mean, I don't know whether before that there was some observation which had some indication of AGN, but this is I could find out by digging out the literature that this is probably the first indication of an active galactic nuclei, this source. And but before 1909, even long before, for example, Charles Messier, William Herschel, their lifetime you can see, and they describe this as star clusters. This is a galaxy, and moreover, it is an active galaxy, and they describe this star cluster at that time. This is the source, NGC 10, whatever NGC 1068, which has been imaged with recent. Of the telescope, absorption lines you can see. And overall, this continuum will go somewhat like black body spectrum. Largely black body, some little bit deviation might be there, but largely it is black body, and on top of that there will be absorption lines. This is the characteristics. These absorption lines are the characteristics of the star spectra. Therefore, if you expect a galaxy which is combination of stars, if you think of, then there will be a lot of absorption lines. So that would not cause a lot of a problem. But if there are emission lines, then it may create problem under certain circumstances, though not all circumstances. So those circumstances are what I will be discussing that. So this is the spectra of a star-forming galaxy. This is the spectra of a star-forming galaxy. You can see a lot of emission lines, and there are a lot of absorption lines. So absorption lines are stars absorption lines, but emission lines are from what? I mean white. And then if it is there, then what should be the width of these emission lines, and how do we explain that? Those are the questions. For example, emission line could be there, as I told you, because galaxies are not only collection of stars. There are H2 regions, there are planetary nebula, there are some kind of stellar black holes. All of them will have some kind of spectrum. And then in different regimes of the entire electromagnetic spectrum, you see some kind of emission lines, except the continuum emission. So there are a lot of absorption emission lines. Now this is what I talked about 1909 work, and after that, from 1924 to 1929, Hubble's work actually proved that there are galaxies beyond our galaxy, and our universe extends much beyond our galaxy. So it was proved by Hubble's work. Subsequent work also has helped to establish that, but pioneering work was done by him. And those spiral nebula now we call spiral galaxies. And those are external to our galaxy. It's not the spiral nebula situated within our galaxy. They are external. That is what is more important. Now, 1943, Thapar, he studied 6 galaxies. All of them are spirals. And then what he observed is that some of the lines, hydrogen lines, have width up to 8500 kilometer per second. 8,000 kilometer per second is the width of the spectral line. What is this width, and why should we express it in unit kilometer per second? That I'll be explaining in some of the subsequent slides. But right now, you just remember this is the width of the emission lines. And Thapar attributed this large width due to Doppler broadening, because emission lines are very thin. It should be, because it would be transition from one energy level to the other energy level. If you just take the difference, then it would be the amount of you will be able to calculate the amount of energy and the frequency. But then why is such a broad width? So it can come from the Doppler broadening. I mean, Doppler effect, you know, I'll be explaining it. So he explained that. And now those galaxies which show such broad lines, it's not that all of them have 8,000 kilometer per second. There would be 500 kilometer per second onward, and up to few thousand kilometer per second. And these galaxies now they are called Thapar galaxies after the name of Carl Thapar. And there are other, and they are AGN, active galactic nuclei. And what is this activity of active galactic nuclei, and what is the apparatus lying inside the active galactic nuclei, that we'll be discussing. And it's not that all active galactic nuclei are on spirals. It started like this, but there are regions which are ellipticals. And so to understand what is going on, because you can't see them, you can resolve the nuclear region of the galaxy which is very tiny. In those days, it was impossible. Even today, to some extent, you can say it is resolved for M87 because the black hole event horizon has been imaged. It is nearby, but for far away, a lot of galaxies are there. It is impossible even today to go to make an image which has sufficient resolution to see what is there. And then only way left to infer is to understand and explain the spectrum. So this is one of the spectrum of one of the normal galaxy, and this is some typical spectrum of one of the active galaxies. And you see this, there are very strong line emissions, and here there could be some of the line emission over here, even though it is normal galaxy. But the difference is definitely there that we will discuss a little later. Just let us see, this is normal galaxy, this is active galaxy, this is starburst galaxy. Starburst galaxy means it has the star formation rate very high. Otherwise, it is like a spiral galaxy with a huge star formation rate, and that is why a lot of outflow of gas, etc. there, and those are seen over here. And this star formation will be maybe 1 year, few hundreds, more than 100. 100 solar mass per year. But in our galaxy like Milky Way, it is only 2-3 solar mass per year is the star formation rate. So you can see how vigorously stars are forming over there because a lot of gases are there. And these active galaxy, it could be star forming galaxies like, I mean, it may not be these starburst, but normal like this. These also have some star formation. So it will be star forming this galaxy normal. But at the center, there is huge activity, at which it doesn't have. So this huge activity of the center, how we have to explain that? And scientists are thinking about those things. And that we have to understand. I'm going through history. Without going through history, we could have explained what is there. But it is always quite interesting to go through this historical development that took place and how they could figure out what is going on. So now you can see the difference. You can see the typical spectra of 3 types of galaxies. It's a normal galaxy spectrum, which have some kind of, emission lines, but which may not be so strong or which may not be so wide as much as these AGNs would have. And here it is a starburst galaxy. You see it has very strong emission lines also, besides the absorption lines. Then how do you distinguish between these two? It's very difficult. But there is a difference, and that is why scientists had to think about it. And they were, otherwise, if there is no difference, then they would have said, okay, very strong light coming from the center could be explained by saying that there is a lot of stellar density. But that does not help you to explain this. And that's simply because the nuclei spectra are similar, but they have the difference in the width of the spectrum. You can see I have written here. It is about 500 kilometers per second to these narrow lines are like that, and the broad lines are 1,000 to 5,000 kilometers per second is the width of the spectrum. And here it will be up to 300 kilometers per second, something like that, below 500 kilometers per second. It is the width which help you distinguish between these and these. And what is spectrum? Let's just explain you. You just plot the flux density and versus frequency. Okay, what is flux density? It is the amount of energy coming from a particular source towards you, and when it is coming, you put some kind of maybe area, say suppose in CGS unit I'm saying 1 centimeter square area, you hold it along a perpendicular to the direction in which the light is coming, the energy is coming. Here energy means light. And then within 1 square centimeter per second, whatever energy will be crossing, that will be the flux. But flux means it is integrated over the entire spectrum. But we don't want that. We want at a given frequency, at nu one, how much total energy crossing 1 square centimeter in 1 second. And then that much energy we collect and say that it is the flux density. So there will be per hertz, per unit frequency range. We want that. So therefore, in SI unit, if we do it, then watt per meter square instead of 1 centimeter square in SI unit, it will be meter square, and per hertz is the same in CGS and SI. So then, how much energy per second per meter square per unit frequency range, which is coming, is called the flux density. That I plot in the vertical axis, and in the horizontal axis we plot the frequency, and whatever curve comes, that we call spectrum. And here, this without these spikes, if the rest of the things is called continuum spectrum, and these spikes are called line spectrum. But if it is spike is going up, it is emission. If spike is going down, it's the absorption. And you can see that there is some kind of width over here, how wide it is. It could be much wider. It is narrower, for example, than this. And this width is more or less similar. It is a schematic drawing I've drawn by hand. So these are line emission. It is this line emission which helps you understand that there is something going on, some activity, and we have to explain that in terms of physics. This is a spectrum. You just keep this picture in your mind. Now, normal galaxy, active galaxy is quite distinct, and these have little similarity, but the difference is in the width of these lines. Now, let me explain the width. See, this plot is horizontal axis is lambda or maybe frequency. Let's say this is lambda. Either way, you can plot the spectrum, either lambda versus f lambda or nu versus f nu. Both of them can be called spectrum. Suppose it is lambda, then the width should have been called just angstrom or centimeter or meter. This would be length unit, because wavelength is the length. But that's not the unit we used. Therefore, we should know what is that. So width should be delta lambda, which unit would be either meter or centimeter or angstrom. And if it is frequency, then it would be hertz. But that's not the unit we use. That's because this width comes due to Doppler effect that even Siffer told at that time, and Siffer could figure out. And it was known in the laboratory experiment, the thermal broadening, because of the thermal motion of the atoms of the gas, the line which is coming from the gas gets broadened. And therefore, why not this broadening could be the Doppler effect. So therefore, you know that if some source is going towards this way and some observer is observing from here, he will see that the wavelength is contracted, and some observer which is observing here and the source of the wave is going towards this direction, in the opposite direction, the wavelength gets elongated. This is what is called Doppler effect. So it is like that. The first time when the source releases a wave, it will release a spherical wave front, and in some time it has come up to here. After some time it has moved this way, and then here release the second wave front. These are the crests, subsequent crests I am just plotting. Crest and troughs are there in the wave. I'm just plotting the crest. And then it has moved by that time. And then, then next it has released, when released the next wave, it has moved by this way. And then this is the crest of that wave. It's traveling in all directions. But now if you are observing from here, what is wavelength? You observe two crests, subsequent crests at some T1 and T2. and that if you multiply by velocity of the wave, it will be the wavelength. So therefore, this here two subsequent crests are far apart, so it is elongated. Here two subsequent crests are squeezed nearby, so therefore wavelength is squeezed. So this is the Doppler effect, and this is how it will look. The subsequent crests in different times, which are being released from the source. If you just plot them, it will look like what happened. And this Doppler effect gives us a lot of clues. Even the universe is expanding. That comes from this simple Doppler effect. Had there been no Doppler effect, then Hubble would not be able to understand that our universe is expanding. Then people would have believed in static universe. So how it happens? Suppose this green emission line is the line which is coming from a stationary source. Now it is from a particular, it is the suppose width which will be anyway there, whether it is move or not, suppose. And then now the source is moving away from you, then it will be elongated this wavelength, and therefore we call it redshift. So it is redshifted. That means this line will be shifted from here to here. And this is called redshift, and that is why we see the redshift in various galaxies, which is going away from us due to Hubble flow. And if something is coming towards you, the wavelength will be shortened, and we call it blue shifting. Okay. And if there are a lot of blobs, some is coming towards you, some is going away from you, and all of them blobs are releasing some amount of lines with little breadth. All of them will be combined with this. If you observe all of them together, then it will give you a wide line. And this is the width of the line, which you see broad lines in the AGNs. AGNs, when you see broad lines, they become broad because of this effect. And that I've tried to explain. When it goes away from you, this is theta. Lambda is equal to lambda naught 1 plus V line of sight by C. V line of sight means V cos theta. So this is the theta. And when it comes towards you this way, that means some component will be towards you. And so there will be minus sign V line of sight by theta, V line of sight magnitude if you only take. And then it will be minus sign, it would be reduced. So it will be blue shifted. And when all these blobs are coming from, which is just moving around, some of them will be going away from you, some of them going towards you, and therefore you see the blue shift, red shift, and all of them very close by, and this entire width will be extremely broad. This is how, or it could be also some amount of broadening could be because of the thermal motion, because every atom is a source of the line when they are emitting a line in a gas. So some of the atoms is going away from you towards you, that also broaden it. So you can interpret two ways. One is thermal broadening, and other is broadening due to some motion of the blob. So if it is thermal broadening, then this velocity dispersion which will come because of this velocity, it will have some dispersion, and that can be calculated by V square mean minus V mean square. V mean square would be 0 because some is going, some is coming, and it will be 0. So then this dispersion will be related by temperature. You can find out what the temperature of the gas. That is how help you. Now you see. Now when Seyfert got, scientists are thinking how to explain. Seyfert got these wide lines. He had to explain it. So for normal galaxies, delta V 100 to 300 kilometers he got, and the H2 region's temperature is 10 to the power 4 K. If you put that in that formula and find out what the delta V would be, it is only this much. Then how can we explain this? It is because of rotation of the galaxy. Because of the rotation, there is a bulk motion, and that within that H2 regions have some kind of temperature. So there is thermal broadening due to this. There is motion of the blobs, and due to that broadening due to this, then you get this much temperature. But there is no way to explain this 1,000 to 5,000 kilometer broad lines, which is coming from center of some of the galaxies. And if you just fit in by this formula and find out temperature T by 1,000 kilometer to 5,000 kilometer or 8,000 kilometer, whatever, then the temperature you get is 10 power 7 K. So no hydrogen atom will give you lines, H alpha line, with this much temperature. It will be fully ionized, and that will give you thermal Bremsstrahlung continuum emission. It will never give you line emission. And therefore, this thermal broadening will not explain these wide lines which you get from the center of the active galaxy. And that's made you think that there could be some kind of motion of the blob. But if there is a motion of the blob, then stellar motion kind of motion, if it has to have within the bulk of the thing, they could not explain with that much velocity. But you need a very heavy object at the center. And that's what people started thinking from 1943 to 1967. And through a lot of arguments that you can see it later from this slide, which will be there in the YouTube, I just conclude that he first proposed that there should be a supermassive black hole at the center of every galaxy. Once he put that, then rest of the things is very easy, because you know there is accretion process. If there is accretion, then matter will be, gravitational potential energy will be released because of the accretion process, and that can give you such a strong glaring light. And the lines will be broadened because of the Keplerian motion of the gaseous blobs or the gas which is moving around the black hole. And that velocity they could get 1,000 to 8,000 kilometers. That velocity spread comes from there. That should explain. So you don't need that much temperature so that the gas completely gets ionized. And later people figured out, since we don't have much time, I'll be skipping that. I'll give you some historical perspective. Do I have time? How many minutes? Hello?
Yes, sir.
How many minutes time do I have?
So it's up to you. We probably thought it would end by 11:30, but it's okay if you want to extend
in 2-3
a bit.
minutes I'm just finishing. Okay.
Sure, sir. Sure, sir.
So now people have constructed this model where there is a supermassive black hole. Matter is falling from surrounding some structure which is called torus-like thing, which will be rotationally bound about the black hole, because otherwise they cannot exist. They will fall radially otherwise. They have to, if they have to remain, they have to rotate around the black hole. And from there, matter will come in because of the viscosity effect, because it is gaseous, it's not solid thing. Our solid body, individual bodies are moving, and therefore they will come via this. And because of the viscosity, there will be a rotational, differential rotation, because at every radius Keplerian velocity is different. As you go inside, Keplerian velocity will be, speed will be faster, and then it will go in and fall into it. And while falling into it, there will be drag between two subsequent layers in the disk, which will give you friction. Friction will heat it up, and if it is reasonably thin accretion disk and reasonably dense, then it will be optically thick, in the sense that the photons which is generated inside will be randomly scattered very many times before they come out from the surface. As a result, the radiation gets thermalized, and what you see is the black body radiation. But at different radii along the disk, the temperatures are different. Therefore, it will be black body radiations of very many temperatures, which will be superposed on each other. And therefore, this is called the modified black body radiation. If the accretion takes place in a very efficient manner, or via a disk, what is called standard disk, which was discovered by Sakura and Sunaev in 1973. Sakura-Sunaev disk. You can read about it in internet, or in later on, if there is a better chance, I can explain you more detail about these things. And then some of them ejects jets because of some mechanism which is yet dispute. Yet not yet settled. But there are some theoretical models. It has not been verified which model works. And then magnetic fields perhaps collimate them, and that's what gives rise to some kind of lobes which are called radio galaxies. And this is the radio emission from the center, which is called core. And this is the standard picture now, canonical models of an AGN. There is a torus, then there is a disk. At the center, there is a supermassive black hole. Some cases there are jets, not always. This is a composite model. But some cases you don't see torus, but there is accretion. It's not via standard disk, and then there is jets also. So it's a composite model. All components are not there in all AGNs, but if we put all the components in a single AGN, it will look like this. This is situated at the this is situated at the center of a galaxy. Any galaxy, if you take the center, it is there. Thank you very much, and I'll be ready to take questions.
Thank you so much, sir, for this amazing lecture. Now I'll be reading out the first question. How do the rotation of galaxies are calculated? How are the rotation of galaxies calculated? What if the galaxy is not in line of sight to us?
How the rotation is calculated and?
What if the galaxy is not in line of sight to us? What if it's not in our line of sight?
No, any galaxy when you will be able to see it, then there must be a line of sight. It is falling, otherwise you won't see it. If it is behind some other galaxy, exactly behind, then it would be difficult to see it. But some cases you might get some of the lights coming from there, and you can try to infer it. But if you don't see it, you don't know whether this is coming from behind some galaxy different, or that processor that emission is generated within the foreground galaxy. You don't know this, but generally that doesn't happen too much. I don't know of any that there is behind something there is a signature, but you never seen it. And rotation of a galaxy can be found out from the rotation curve that has been discussed in the previous talks. And and if you plot the rotation curve, that velocity, okay, the rotation curve, how do you generate? That also comes from this Doppler effect. You suppose, for example, you take a spiral galaxy which is rotating. In general, they will be rotating. Then you observe in a line, for example, H1. If it is radio, then H1 emission, which is 21 centimeter emission because of the spin flip of electron and the proton of hydrogen. If there is a same spin is higher energy state, it will flip to opposite spin. It is lower energy state, and it will emit a photon 21 centimeter. And through that line shift, whether you are taking, if there is a, this is the galaxy. Let me just draw it. This is the galaxy rotating this way and this way, and you are observing from this side. And then when you are observing this thing is coming towards you, so it will be blue shifted, and this side is going away from you. It will be red shifted, and then from there you can calculate the velocity. I mean, you have to take a correction for its overall Hubble flow velocity. That you have to subtract that effect. Then because of this blue shift, red shift, you will be associate this with the velocity, and you can calculate the rotation curve. And from there, you know that it is rotating. Is this what you wanted?
I hope the answer is clear. If it's not, you can write it in the chat box. So, sir, the next question was that, could there be a galaxy spectrum with no H alpha line at all?
H alpha line would be there, I guess. because if it is there would be something, whether you detect it or not, it might be question maybe, because if it is star forming galaxies, spiral galaxies, then there will be some H regions which will be emitting H alpha. If it is elliptical galaxies which do not have star formation going on, do not have any gas, do not have H2 regions, but it gives rise to then I don't know, there could be no H alpha, but or maybe very weak.
Okay, sir. Thank you, sir. So the next question was that, in which wavelength is the AGN luminosity mostly measured?
Okay, they may not, they may have some problem maybe. You can go to
Ishita, can you just repeat the question for sir?
Sir, the question was that, in which wavelength is the AGN luminosity mostly measured?
No, AGN luminosity, it's not in all measured in entire electromagnetic spectrum. It's not a single frequency, it is always measured. In radio, you get a wide range of radio frequencies where it is radiating. You constrain a spectrum, we do that. But in optical also, you can do from optical and UV together from 2,000-3,000 angstrom to 5, 6, 7, 8,000 angstrom. You can be able to get the spectrum. And in X-ray, you can measure it from 1 kV to 100 kV. And above 100 kV, you get in gamma ray also. So everywhere it is radiating. But question is where it is peaking. That depends upon the nature of the things. And also, when you don't know the nature, you just do a survey and you see where you get it. Then depending upon your science case, you target your frequency, target a source with a chosen frequency, then do your science. For example, if I want to do how much is the radio jet power coming from a particular source, and I saw that it has, from the literature, I saw 10 megahertz to 1420 megahertz data are there, and above that I don't have. And I have some science for which I need to know the spectrum beyond 1000 megahertz. Then I will target those sources at say 5 gigahertz, 8 gigahertz frequencies with VLA or JVLA telescope, and then do my science. So everywhere it is radiating, and some cases, of course, which is radio quiet, they will not have much of radiation in radio, but I want to study the accretion related some problem of that AGN. Then I will observe it in X-ray band with X-ray telescopes. For example, now we have AstroSat, we'll be doing that with the AstroSat. We can do that with the AstroSat. So it depends upon your science case and where that particular AGN is radiating most, which phenomena is dominating, etc. It's not a single answer that, okay, I will observe this because I want to observe AGN. Various AGNs have various properties. Is that clear?
I hope the answer is clear. So the last question is that Biswajit is asking, I have a general question. Suppose I am standing on the surface of planet, example Earth. For me, everything seems flat from the surface until I reach space and view it from above. Then I perceive my planet to be a sphere. Similarly, how do we know the structure of our galaxy? How did scientists determine a location within the Milky Way galaxy? In other words, how do we know that our solar system is in the arms of a spiral galaxy far from the galaxy center?
Yeah, this is very good questions, but this from the arms, it is very difficult to see the entire structure of our galaxy, and we don't see the structure, the spiral structure that we see for the extra galaxy. For extra galaxy, we can see the spiral structure of that, but the similar kind of picture we don't see for our galaxy. But then how do you know how the structure of a galaxy is? Whatever picture you see in the internet about our galaxy, these are all based on some observations, but then after that it is drawn by hand to some extent. How do you observe it? You may not be in a place where you don't see beyond that arm. Maybe some other arms from the galactic center you can see slightly off disk, our position could be, and you can see our galactic center, because we know where the galactic center is. From there, some of the arms it is visible, and we see that. And then you collect all other properties of the star formation, these, that, etc. And then whatever you are seeing, some Perseus arm, this arm from the galactic center, when you image it in radio, whatever you can see it, from there you now apply the projection effect mathematically. Then what could be the structure, so that you would be able to see whatever you are seeing, and then you concoct the picture. I mean, it's not concoction in a way, but it's if you figure out the picture. You figure out the picture and say that, okay, this is what galaxies could be looking like this. But it's not a direct image with all the arms and the disk, etc. As has been portrayed, you directly see it. You don't directly see it. You have to just figure out with a lot of effort.
Thank you, sir.
Yeah, even if you don't go out of the surface of the Earth, still there are ways to figure out that Earth is round. And when people didn't go into the space, and still people could figure out that Earth is round. So the similar way, there are ways to figure that out.
Thank you so much, sir.
Can I add to this question?
Yeah,
maybe.
please.
Yeah, so possibly, we cannot see beyond a certain region mainly because of the dust obscuration or the obscuration of other light sources that are present in our disk of the galaxy. So the way we measure, for example, the way we measure the orbits of the center of our galaxy, also there are certain wavelengths in which the dust obscuration is not very prominent. It's not zero exactly, but it's not very prominent in that situation. So say for example, there are certain particles also which can be seen directly. For example, neutrinos, though we cannot determine the direction of from where the neutrinos are coming from, but they come unaffected by other objects. So there are other observations also which you can do and kind of deduce the structure of the nearby universe. And of course you have the dynamics and other effects that are happening. You have globular clusters which are above and below the plane of the galaxy. From there you can make out your own position in the galaxy, in where you are in the galaxy, and things like that are done. So it's not just one observation you make and you see whole galaxy as you see for extragalactic sources. It's a combination of various observation mechanisms that are there.
Yeah, I think Mamta has given very good answer to this question.
Thank you, sir. Thank you, ma'am, for answering these questions. That was all the questions. Now, before we move on to Anand's lecture, I would request everyone to turn on their cameras so that we can take a quick group photo.
Oh, 1 minute, please.
Thank you, everyone. So now I would like to call Muskan. Muskan, are you here?
I'm here. Next up, we have Dr. Ananda Hota presenting a lecture on black hole galaxy co-evolution study with GMRT and Rad at Home. His stroke of genius, Rad at Home, is the first Indian citizen science research platform in astronomy. Apart from this, he is also a UGC faculty at University of Mumbai Department of Atomic Energy, Center for Excellence in Basic Sciences. With some remarkable accomplishments in the field of astronomy and astrophysics, he is also an elected member of the International Astronomical Union, Paris. It's an honor to have you here, sir.
Thank you, Muskan. Thank you very much. Welcome, everybody. I'm kind of a host here also, right? So thank you, just not Muskan, but all the team leading this activity. I cannot recall everybody's name, but certainly in every activity, there is a big team that is always involved. And thank you, Mamta, for leading this activity. Probably some students wrote me back much before the last month or so. Finally, we are having. Thank you, Chiranjeev, for joining also. So we are having, actually, both of you have given very nice introduction to what galaxies are, what the line and the accretion and the how do you interpret the physics behind galaxies. That's what you have started. Unlike many other talks that is easily available from big institutions, we are actually in this, because this is a workshop, we are kind of focusing on small details so that your practical understanding improves. In many automated tools, you learn less but finish the job. But in less automated manual job, you actually learn the details. One instrumentation astronomer actually told me that everybody understands the importance of nut and bolt, but we often ignore the importance of the washer, what is in between them. So unless you do the practical part, you miss the what is the critical point there. Tiny mistake can screw up everything. So it's an astronomy talk. We will not talk mechanical engineering. So as you can see that GMRT and Rad at Home is two catchword in all these posters. What is very important is, in few days back, GMRT was recognized as the third milestone in physics that Indian science has achieved, after J.C. Bose radio communication and after C.V. Raman's Raman effect. Third milestone that IEEE has recognized. There was a dedication ceremony and the big event there. All the newspaper covered it. So definitely you all who will learn now the little bit of science with GMRT, you are proud. But at the same point, what is the purpose that Rad at Home is coming to you is that how you can not only practice, not only learn, but also contribute to some extent what science discoveries can be done from Indian soil. That way, we are not here just for the education part. We are here for the research contribution part. So giving practical detail to every pixel there, every line that is drawn there, and the hands-on session in the afternoon would be very important. Picture is not just a picture, it is actually a matrix of numbers, right? X, Y, and the Z pixel value. So that is what actually we are going to have to learn something in this workshop. That RGB image is just a tool, but it is a multi-wavelength data that is presented in this color picture. Contour is just a tool that we will learn it slowly. So 30 people or so that who have already submitted their RGB images, you would have got certain kind of touch that what we are looking at. It is not the Milky Way galaxy picture that you take with your mobile phone. It is something else. It is not just the stars in the sky. It is something beyond that, right? So what is not visible to naked eye, what is not visible to just optical, all the wavelength possible we want to actually accumulate and learn. The very standard example that I give, that when you go to a doctor, you have a problem in your body, doctor will try to apply all the diagnostic tools possible to solve your problem. For example, take a visual image of your part, take an infrared image. It can show the blood veins actually. Take an X-ray image if your bone has broken there. Take an ultrasound if there is a problem in the flow of the fluids inside your body. Blue shift, red shift. Try to understand the Doppler photographs anybody has. It gives you acceleration, it gives you velocity, which part is blue shifting blood, which part is red shifting blood. So all kind of imaging and dynamic spectroscopy we apply in all wavelength possible to have a best understanding of whatever is there in the sky. Okay, so I tend to get diverted to giving this kind of thing, but to focus on what we are going to learn, let me share my screen. Can you all listen my voice clearly?
Yes, sir, it is very clear.
Thank you. Can you see my presentation?
Yes, sir.
Okay, great. So now, as you can see in my cover page, there's a lot of information, right? And a lot of information is because this talk is a result of so many people, so many institutions, so many thought process that has gone through. It's impossible to give this talk without acknowledging all those people. I see my video is frozen. Can somebody confirm if it's listening properly?
Sir, it's not frozen.
For some reason, my video is frozen to me. Anyway, doesn't matter. So I will come back to this thing. This is what we are at. Thank you for hosting Red at Home workshop, because this is a citizen science program. Whoever provides an opportunity to get connected with citizens is actually helping everybody, is helping the nation's scientific growth. Thank you for joining this Red at Thapar Institute. So many people have shown interest. So many people are interested to learn. So many people feel proud about their GMRT heritage in some sense, you can say. And they are excited to be part of that science that the GMRT does, the discoveries that GMRT does. This is what the cover page is now showing. That you all recognize this icon of black hole now. Event Horizon Telescope's image become icon. Everybody loves black hole, Big Bang, and alien, right? So what is Red at Home is going to do is bring this kind of physics, this kind of astronomy to your laptop, to your desktop, to your home. What is that? This is an exotic galaxy, Speca, that Chiranjeev, me, and few other of my colleagues have discovered. They made a lot of news, probably the first international news-making discovery from GMRT data. That all the plasma ejecting relativistic talk because of lack of time. But the plasma ejecting galaxies are almost always elliptical. But it's the first confirmation that this is a spiral galaxy. So we named it Speca, and people got excited. There are many exotic things happening in this thing. On this, that when the plasma coming out from the central black hole accretion process, the green part, how it is going to affect the surrounding galaxy, the gas content there, the shock hitting there, the X-ray emission there, the infrared emission of star formation there. There is a beautiful example. Give a lot of connectivity with people, and they are actually asked that what kind of discoveries, whatever discoveries we are able to, how can we involve students of our country that they can also join in the discovery process with the GMRT. They can also join in contributing some understanding of galaxy evolution that we are trained during our PhD to do publish paper. So this is basically the science, galaxy and black hole science, that we are going to contribute to the scientific discoveries in this field. And very interesting question that kind of troubled me for a very long time is that they want to open a galaxy, Google, and ask for galaxy. Almost always get a picture of a galaxy taken by Hubble Space Telescope or American or European telescopes. Where is the image? Why we are not able to contribute? The moment you type astronomy in India, it's almost always the ancient astronomy, Siddhantic astronomy that comes into the news. I feel like I want to change this image. Okay, I want to change this image. So what is the competitive edge that India has? Right. So what is the competitive edge that India has? I thought it is just number of science educated English communication young with the internet. Right. So this is what I thought, that can I involve all the undergraduate, graduate science engineering people in this field of study and give them, empower them the power of the GMRT telescope. Right. The moment you give them the power of the telescope, they don't no longer have a microscope. They have a microscope now. They can see many more things. They don't have a toy telescope. They have a research telescope in their hand now. This and launch this, lot of institute. UGC salary that I get, CBS, Institute of Physics, TFR, NCRA, ICTS Bangalore, Institute of Science Bangalore, Vigyan Prasar, and Nehru Planetarium, HRI, Astronomical Society of India, NICER, various, ICER Berhampur, NICER, ICER Kolkata, IIT Banaras, everybody is coming to support this activity. How do you train people in contributing to science? This is what is called citizen science. So earlier we were only training people when they gathered there. This is what is the session, all the YouTube thing now, all the Facebook thing now, that people are getting trained online wherever they are. And you will be helped. Today it is ODRAW, one-day training program. You will be helped, you will be mentored by the people, by the e-astronomers from Rad at Home who have been trained for 7 days in all this institute that has been supporting our thing. Okay, let's move now. These are the e-astronomers who will be helping you in the last session, up to the last session. Preet, Akshat, Dviti, Vishwajit, Rohit, Chandan, Asutosh. So the first 3 lectures are going on. This is the schedule. You will be given a kind of a demo how to make those RGB images and contour images using online tool. We have made a small RGB-maker tool. We'll also give alternate ways of making those RGB images and contour in NASA Skyview. This is where we started actually in 2013. There will be break. We can, after that, whatever images that you will be making during this demo session and whatever you have already made since yesterday, we'll be discussing them one-to-one with you so that you improve your image analysis and you understand what you have made. What does the GMRT shows? What is that white line contour drawing is? Why these contours are different for different galaxies? Why certain galaxies are seen in radio but not in other galaxies? Why my big bright galaxy seen in optical UV-IR is not seen to radio? How do I understand that? That particular session will be post-launch session. Even people watching me in YouTube live, they can also ask questions. They can also show their post in the Facebook group. We'll take up their question, we'll take up their images, and we'll discuss here so we can listen. So then, based on all this activity, we will be selecting few people because our resources are limited. We'll be only interacting with few people, selected people, but in the last session, but independent of who are selected today, they all can join Facebook group for the citizen science research for several months, several years, whatever you wish to. Okay. This is basically the third talk of the morning. The outline will be, what is galaxy evolution? I will be talking. How do you age date determine the time basically of the star formation process? How old the stars are, how old the star formation happening in this galaxy, and how old the black hole activity happening looking at the radio primarily. What GMRT detects that you can tell that when the black hole was active in creating this relativistic plasma. Chiranjeev is an expert in this process, in this study of age determining of the black hole ejection. I kind of specialize, you can call, in understanding this kind of black hole, galaxy, star formation, AGN activity, how they are evolving and how to observe them. So especially for you, how can you participate through Red at Home that you will grow in your career and will contribute to science discovery? We'll have last half of this. 1 minute break. Any question in between? The organizer can ask if they have something, if everything going fine. You can listen and everything going fine?
Yes, sir. Yes, sir.
Okay, go ahead.
Yes, sir.
Okay, good. So as I said before, the moment you listen that we are doing astronomy, we are counting stars, people make joke about that. But in this talk, we will not be understanding stellar astrophysics, stellar science. We'll be going beyond that. You all know, for a quick review, that we observe the sky with big telescope, not 1 inch, 2 inch handheld telescope, that big observatories. You won't be allowed to watch through this telescope with your eye. I want to see Saturn, I want to see a galaxy. That kind of subjective observation of astronomy is over. Everything is recorded in computer so that everybody interprets the data samely. Everybody sees the same thing. I see the ghost, somebody else doesn't see. It doesn't happen that way. Yeah, in Galileo's days, they used to observe through the naked eye, through the telescope, and draw it to present others that what do they see. The discoveries of planets, satellites around Jupiter, it's drawn in hand. All the stars that you see, stellar tracks that you see, they're different brightness, different color, primarily because star can be considered a black body and the surface temperature is different. Blue looking objects, blue looking stars are massive, O and B type, 7,000, 8,000 degree hot basically on the surface, and they survive for only a year. Sun star, billions of stars will be sunlighting, and they are 1 solar mass, 2 solar mass. The blue stars could be 10 solar mass, 20 solar mass, right? So their temperature, their lifespan, their color are different. In radio with the GMRT like thing, you see various kind of plasma basically hanging around in the space. Most of them are actually ejected out of the central galaxy at the central black hole process. I wish we could see all the wavelength, then we could have seen the sky very differently. What is important here is that these are not star-like systems, they are not black body, they are not atom molecule. You cannot define a color for them, they're just pseudo color. So RGB image analysis that we will be doing today, important point to understand is we see the stream, we see the brightness distribution in only 3 colors. So we will represent various data which are UV, X-ray, radio, infrared, they're invisible. They don't have a real color that human can define, but we will represent them in the false color image. So the basic scientific motivation you can call is this. This bottom picture you have seen in all the previous 2 talks by Mamta and Chiranjeev, that this is various kind of galaxies. And why they have come in varieties is because something would have happened in the past. Everything started from the hydrogen, from the Big Bang, right? Something would have happened on the way in the 13, 14 year evolution process, in the cosmic evolution, that they have become different kind. This is the beginning. This is the seed basically thrown on the ground And all the seeds have grown to big trees, like thing they have become galaxies. So what is this? This is a cosmic microwave background radiation picture image. You can say the first picture of our universe after Big Bang. Big Bang we cannot take, but this is what we can take. Every radiation that you see in your TV, in your analog, the Ramayana Mahabharata era analog TV, the black and white dots that you see, jilmil, so many kind of insects moving all around, that has few fraction of them is actually this Big Bang. The CMB picture that you see is also a black body whose peak is around that 3 degree Kelvin. So it has radiation not only in that microwave band, in the radio band, where the TV is working, but it also has radiation in the infrared, it also has radiation in the low frequency everywhere, because it is a black body. It is taken a black body spectrum space. Say there is a peak around 3 only. So what is this color picture is saying now? There are some regions in the universe, it is seen all part of the sky. Galactic effect, individual galaxies have been subtracted. This is the Big Bang relic, you can call it, right? So the color representing the temperature differences. They fit a black body to whatever radiation they are getting in different frequency. And what is the peak shift there? Where is the peak shifting? Left, right, middle. So they are distributing that kind of peak differences, the temperature differences, peak emission differences, and telling where the radiation is more coming, where the temperature is high. Wherever the temperature is high, the temperature difference from the background is high, that is going to accelerate the radiation, cooling by radiation process. So that cooling, wherever the temperature difference is high, it will cool at a faster rate, d by dt difference in T. So that way, that region is going to cool down, means gravity is going to work faster. Individual molecule atoms will now attract each other, and the thermal jittering or bouncing each other, that will slow down. I was muted for some reason. So if the gravity is going to take over, whatever was there is going to collapse and slowly form hydrogen gas cloud, hydrogen molecular cloud, small dwarf galaxies. Big gaseous molecules, big galaxies are formed by merger of those dwarf galaxies. Spiral galaxies have formed. Now the spiral galaxies, as the universe is evolving, they are going to merge to each other and then can become elliptical like galaxies that you see on the left. So that precisely is the universe's galaxy evolution. Now, like from the single cell amoeba like creature, you have become plant and animal. Huge diversity of galaxies that you see today. They are very different kinemechanical nature, different star forming nature, different black hole nature, different shape, etc. It's because of the evolutionary history, interaction history has become different for them. So from the seed distributed, we have grown different kind of diversity trees of galaxies, you can call. You all know the merging galaxies, interacting galaxy, antenna, etc., etc. Beautiful spiral galaxy from HST picture, beautiful elliptical galaxy. Notice only the difference. Here the color is real and optical. Here all the stars are like sun, so that the peak of the emission representing its color is yellowish. A spiral galaxy, on the other hand, there are regions where a lot of star formation is happening, lot of gas is compressed there, lot of stars which are O and B type, or peak of the emission is bluish. Here the stars are cooler, so that peak of the emission is yellowish there. Okay, this is what is actually, we should realize that different galaxies are having different population, different age of stars in them. And O and B type hot stars survive for few million years, and this kind of stars, sun-like stars, survive for several billions of years. And this kind of stars are in small amount, is also there in the central region. Okay, so how the galaxies are distributed from here and here that you see in detail, I want to show you in a quick video how the galaxies are distributed. Okay. in the next video, I will show you. Let me, we don't have much, no, we should watch it. This is what is the simulated, mathematically, physics-wise simulated creation of our Milky Way galaxy. Cloudlets, which will have some angular momentum, so that's what they are rotating. When small clumps actually keep rotating and merging, their orbital angular momentum is actually creating, and they are forming kind of a disk. And such smaller and smaller thing creating bigger thing. Now they are also going to merge. They will make even bigger galaxies. This is what could be Andromeda-like, Milky Way-like galaxies merging. Right? So let's stop it here. But notice here that the pink part that you see, white part that you see is the stars in the galaxy. What is there is this bluish, greenish thing all around. This is the hydrogen gas. So if you look at the hydrogen gas 21 centimeter line emission, quantum mechanical line, at the ground state, protons and electron spins are parallel or anti-parallel. They will have higher or lower energy state. They will try to become the more stable state, anti-parallel state. And the energy difference is so low that the h nu, del E h nu, if you equate, nu comes to 1420 megahertz, 20 centimeter, roughly 21 centimeter radio line. So if you observe that the galaxies, the Andromeda or M31, anything, then you will see this kind of hydrogen gas surrounding them. 3, 4, up to 10 times larger region, you will see the gas in the galaxy, which are actually coming closer to the center, and when the density grows, they form star. This is what was happening when we were trying to grow galaxies. Galaxies are glowing in optical, but the gas is much bigger that is glowing in the radio band. Okay, coming back there. This is all something similar Mamata also showed from the Hubble Deep Field. Here you see so many varieties of galaxies in tiny part of the square, tiny part of the sky. They are of different color, different structure, different distances as well. Here, there are galaxies which are, say, very nearby. There are galaxies which are too far and looking small and reddish. So nearby galaxy is emitting some light. Light may be taking 1 billion years to reach Earth or the Hubble Space Telescope. From a little yellowish and farther away object, light may have taken 5 billion years to reach the Hubble Space Telescope. From here, light may have taken 8 billion years to reach. From here, which is the tiniest yellowish thing, what you can spot, maybe even tiny than that. Light may have taken 10 billion years to reach us. So what are you actually observing? You are observing how the galaxies were looking 1 billion years ago. You are observing how the galaxies was looking 5 billion years ago, how the galaxies were looking 8 billion years ago, how the galaxy was looking 10 billion years ago. You have one picture which is telling how the galaxies were, how the universe was at different time in the time travel way. This image is a time travel. This is what we are trying to understand. So now you will sort it in different boxes. What are the behaviors of the galaxies that we see 1 billion light years away? What are the behavior of the galaxies that we see 5 billion light years away? What are the behavior of the galaxy that we see 10 billion light years away? And try to understand if there is any change in them. If there is any change in them in their statistical nature. Here is somewhat that kind of a study, that when you sort the galaxies, today, redshift 0, roughly 14 billion years after the Big Bang, almost all the galaxies fall into two boxes, either spherical like elliptical or spiral. Very few are in the confused in between type. But when you go back in the history from that picture, you can sort the galaxies which are 9 billion years after the Big Bang. You can sort out the galaxies 5 billion after the Big Bang. You can sort the galaxies in 2 billion years after the Big Bang. At different redshift, 0.5, 1, 3.5. What you notice here, that most of the galaxies, when you go back in the time, they are losing their classification value. So here it's difficult to say they're elliptical or spiral. Here we are completely lost. Here similarly it is difficult to say spiral or not. Here somewhat like spiral, but you cannot decide really. They are at the formative era of their life. If you say this is a tree and this is a animal, here the galaxies are not yet decided they want to become a tree or a animal. Why? The interaction has not happened in that way that they will either become this or become this, following the specific physics principles of gas, electromagnetism, or nuclear, or whatever, gravitational, all the force applied to their interaction. This is one more very important thing, usually not seen. That's why you need to pay a little focus. This same redshift, nearby zero is our own nearby universe, far away, back in the history of our own universe. What we are observing is their star formation rate per unit space volume. M sun is solar mass. How much amount of gas is converting to star, that is what roughly is measured by various ways. Multiple methods of doing. Madhav's famous plot actually is one. So what is seen here? The star formation rate density is kind of increases if you start looking far. It reaches a height and after that it starts falling down again. So the star formation rate density in our universe was actually low. It increased and it declined again. It has become lower and lower by today. So something around few billion years after the Big Bang, redshift 2, or around 10 billion years of look back time, the activity in galaxies was the highest density. They were forming per unit volume, they were forming high rate of stars. And what happened after that? That the rate has declined. You may have heard a recent Nature paper published by Indian astronomers. In Thapar Institute also, Nisim gave a talk from an NCRT IFR, Nisim Kanekar. Their group have measured the hydrogen content of galaxies very far. You may not have noticed this thing, that radio astronomy from India is contributing a big thing actually. I will tell you the why. When before GMRT, there is a telescope called UT radio telescope. From that small small Uti hill station, the Govind Swarup, the famous who recently passed away, he is considered father of Indian radio astronomy. He is leader of building both the telescope actually. So in using that Uti radio telescope, Vijay Kapahi, an astronomer from NCRA then, or Uti telescope, they measured the number of radio emission having galaxies far away and nearby. Like this, very similar to that. How many galaxies you can see with UT telescope nearby, how many galaxies you can see with UT telescope far away. And they proved in their paper, there is very clear evidence for the first time that the number density of radio galaxies far away is different. That was a very strong evidence against the steady state model. So it is a very strong evidence for Big Bang model. A lot of people know, that's why actually the contribution from UT group with Kapahi's paper. Today again, this kind of thing, that because of our sensitivity, GMRT sensitivity 3 times bigger collecting area than American telescope VLA, we are able to make best sensitive hydrogen gas content of galaxies far away. And with that, we are able to find out that what is the gas content of galaxies then, what is the gas content of galaxies today. And can the gas content be the clear reason that why the star formation was high then and is declining by now? It's very similar actually to the black hole activity also. Black hole activity is also very high around this redshift 2. Number of quasars, number of radio galaxies, everything is high. So star formation is high, AGN activity is high, accretion is high. That's why some people start calling this epoch of our universe as cosmic noon. So what we are looking at, the radio sky survey that you will be looking at, this radio images that you will be seeing, there are maximum number of sources around this redshift. Can the black hole be the culprit for decline of the star formation? This is one of the scientific aims of our Red Home Collaboratory. How do you achieve it? It's a technical matter, and that technicality is supported by our own GMRT as well as our citizen science method. I'm coming to that later. Let's not repeat, except that when we are evolving the evolution concept, it is important. This is simulation from millennium simulation. Universe has been simulated at redshift 18 or 200 million years after the Big Bang. Remember, 200 million years. Our sun is 4.5 billion years. So see the time scale there. So here actually in this epoch, there can be O and B type stars which survive for only few million years. But from those days, O and B type stars won't be visible now. They are very short-lived. This is simulated redshift 5.7, 1 billion years after the Big Bang. Roughly 5 billion years after the Big Bang, roughly today. What do you notice? You notice that the gas was almost uniformly there everywhere. There was a contrast, some less dense region, high density region, but the contrast has increased significantly with time. There are metro cities like thing, and things are probably gas and galaxies are migrating toward the center because of attraction toward the center of mass at the clusters of galaxies. You must have also heard the Saraswati supercluster that Indian astronomer led by Jagdish Bagchi has published, and it even came in the Kaun Banega Crorepati show, right? So what is that? That there is a slow rate from this. It has taken 10 billion years to reach this level, right? So there is a slow rate at which, some specific rate at which the clusters are growing and becoming supercluster. If you find few more supercluster, that will be trouble. For our estimate that at so early in the epoch, so many clusters could not have formed. So our models must be corrected. Okay, so let me show this cosmological millennium simulation, how things are actually growing in our universe for easy understanding. Notice the redshift or the time after the Big Bang. It is slowly growing. It's a rotating kind of a fly view. So things are coming. The contrast of the brightness at the center is increasing, you can see. Galaxies are distributed in this kind of filamentary or cosmic web, it is called. At the bottom, it's 500 kiloparsec routine. Our galaxy is roughly 20 kiloparsec size. Every blob that you see here is a galaxy. The contrast is growing, gas is getting attracted towards galaxies, stars are forming there, and the galaxies are coming close to each other, forming small groups, and small groups are forming bigger groups of galaxies forming clusters of galaxies. So like the metro cities at the center, Delhi, Bombay. And metro cities are connected to this kind of national highway or filaments. And all the galaxies are kind of migrating through this kind of filament intergalactic interaction, galaxy to galaxy interaction. They want to shake hand and go together and go to the cities. So during the process of forming small dwarf galaxy spiral at the outskirts, what has been happening in this interaction process, that most of the galaxies at the centers of these clusters have actually become elliptical because they have been merged, they have been stripped of their gas. During this migration process from early epoch of our universe to today, what the black holes have been doing, what the gas has been doing, that there was a cosmic noon and then decline of star formation, decline of black hole activity. Okay, so this is what these things are merging and the clusters are forming. You all can watch it later on. So basically this is the point, that star forming spiral galaxies and ellipticals have very little current star formation. Why this is happening, we should understand. And one more important point, plot the mass of the black holes at the center, the mass of the bulge of the galaxies. In a small amount of spherical part, there is the bulge and then the disk, right? So point is, why small galaxies with very little bulge have small black holes and large galaxies with large black hole. Some large galaxies have solar black holes in them. Now that the Nobel Prize has gone to black hole mass measurement, black hole imaging and black hole mass measurement has got a lot of media attention and public attention and students' interest. You should all focus on this kind of studies and point that not because of news that you should focus on, but because of our India is part of 30-meter telescope, square kilometer array, and LIGO, that kind of studies, big major international research facility. You should align yourself to this kind of scientific topic that you can take due benefit of the money that the country is investing in these big mega projects. You have the opportunity to make certain kind of discoveries in physics or astronomy, astrophysics, that maybe you can in a few decades, we will be able to get Nobel Prize, several of them. We will be leading that. So coming back to the black hole effect, I will show you this video. When two galaxies actually merge, star formation increases because galaxies are coming close to each other, compressing gas, and that forms stars because of gravitational collapse. Now these two spiral galaxies, when they are merging, the gas get compressed, star formation happens, the gas get heated up. Now because of interaction, they will pass around and the tidal tail will form, and this disturbance making the stable orbits around the center go disturbed. They will be getting pulled toward, like the satellite falls on Earth, they will pull towards, gas and stars will fall towards the center, density increases at the center, star formation increases, starburst will outflow, a lot of gas is removed from this galaxy. Now the galaxies are going to merge completely. It will happen again, and another blow of removal of gas by the wind, stellar wind, supernova, and radiation pressure from the star formation, the stellar wind. Now the remnant of these two spiral galaxies that has become, it's become an elliptical thing, which has very little gas to form, continue forming star. So this is called quasar feedback, or feedback from the accretion onto black hole. Because of this feedback and negative effect, the remnant of this merger no longer have cold gas or fuel for future star formation. And this is what happens, that you become a elliptical like galaxy, like this you see today. So are forming blue-looking gas-rich spiral galaxies merging with another one can lead to zero star. Sorry. So the third interesting, black hole mass, galaxy color, and black hole mass, black hole activity correlated. Elliptical galaxy, spiral galaxy, their color is correlated. Here I'm telling you something called luminosity function. How many galaxies are there at a certain luminosity range, L and L2 del L. So here is a large number of galaxies. Here is luminosity. Less luminous galaxies are large in number. High luminosity massive galaxies are less of them. Very similar to, like, there are many less income, poor income people, and there is only few billionaires, right? Kind of everybody is kind of a different growth process, of course. So here what I'm saying is that theory is saying the red curve should be there. How many low mass galaxies, how many of them, how many high mass galaxies. Theory predicts the red one. But what is observed is the blue one. What is observed? There are lack of more massive galaxies even at the higher luminosity. For some reason, the luminosity or of these high mass galaxies are not increasing as expected. Here, the way around. Here also, the number of galaxies that you observe is low compared to the theory. Now, people explain this discrepancy by saying that in low mass, maybe the star formation process, the supernova process is throwing away gas. And if they throw away gas, the star formation stops. So if you don't see the thing, then how do you know there's a galaxy? So our observation of finding less massive, less number of galaxies may be an observational bias. Gas cloud may be there, galaxy may be there, but we don't detect it optically. Here, they explain by saying that maybe in the high luminosity, high mass galaxies, the black holes are so active that their radiation jet is so active that it blows away gas and prevents the star formation. That means prevents forming, adding more mass to those galaxies. So they get constrained by kind of a feedback that I have eaten enough, I have grown enough, I don't want to eat more, I don't want to grow more. This is basically black hole galaxy coevolution process. How the galaxy's behavior and black hole's behavior are related by this kind of a jet radiation feedback process. Here the black hole tells the galaxy not to grow further, right? So here comes the role of radio astronomy. Because the black hole throws away some kind of ionized plasma, relativistic plasma, we can observe that kind of relic plasma and understand about the galaxy's black hole history. Okay. We discussed showing jet after the merger. Can we find the smoking gun evidence? Can we find a relic evidence that the black hole's outflow is still there, which is of the time scale of the decline of star formation in a galaxy? Let me repeat. If we can find a relic evidence, smoking gun evidence of black hole's outflow, plasma outflow with GMRT, which says that 500 million years ago, this plasma was there, active and glowing. It has been cooling since then. Can we say 500 million years ago, same time, since when this galaxy is not growing star vigorously but has declined? Cause and effect, can you link? This is what citizen science actually comes in. That in optically, a school teacher found this kind of a fuzzy faint thing. And that time people did not know actually what this is. And when they looked at this is a quasar, dead, long dead quasars, relic emission. And she became famous, she became author of the paper. This is what is citizen science most celebrated thing. She became a celebrity just with one click saying that, what is this stuff I don't understand? What is this faint fuzzy thing? Here I am giving the analogy that Indian appreciate, making a bridge. Forget about the meaning, but the story is that the squirrel contributed by throwing sand on the bridge made by big rocks. It is important, however small the contribution is important. Without she spotting this, nobody knows if this could have been spotted by astronomers. Astronomers had no idea till then that such a thing actually exists, such a phenomena exists. Because the galaxy is no longer a quasar, the black hole is not active there. It is stopped. But this is the smoke, this is the relic remnant that was detected. And spotting this kind of thing is difficult because they are faint and fuzzy and irregular in structure. Automated algorithms struggle in that way. Data amount is huge, so we all can contribute. Okay, so I should try to close. I guess I started around 12 o'clock. What time I started? Can somebody remind me?
12 o'clock, sir, 12 o'clock.
Okay, fine, not bad. So here is the plot of the flux that Chiranjeev has already explained. Whatever energy you receive per second, per unit time, per frequency range, so that the measurement is a function of color or waveband. At the bottom you see far UV, near UV, close to ultraviolet, green, red, near infrared, and J, H, K bands sit around 2 micron. From optical, UV to 2 micron. Every band measurement, how much energy a galaxy radiates, is measured in different filter, different bands. And what is plotted in the color lines here, these curves are showing the nature of stars, how old they are. Okay, this basically the color is coded at the right hand top. You can see if this is looking like kind of indigo color, blue color, green color, yellow and red, they represent stars of different age. Okay, now you all know that sun is like 4.5 billion years. Okay, and this emission falls in yellow, peak of the emission, black body spectrum. Lambda max t equal to constant. If you want to put lambda max will be yellow, you can find out the t, right? And age of the star you already know. So suppose a galaxy is made up of 100 billion sun-like stars, only like our sun. All of them will be yellow, all of them will be old. So the spectrum will be from ultraviolet to infrared, whatever you observe is peaking in yellow, right? So if a galaxy spectrum fits the black body like thing, the spectrum like thing, which peaks around yellow, it may be made up of 100 billion sun-like stars. If it is a Cirrus or a blue star-like thing, suppose O and B type stars, which survive for only few million years, okay, then the color of that galaxy will be bluish again. So observe a galaxy in far UV, plot its brightness, infrared, and it's it. This is called stellar population. Looking at their emission, you can figure out intensity weighted what is the age of the stars in that galaxy. If its age is sun-like stars, billions of years old, or its age is few million year old star formation happening there. Okay, this is what is a radio galaxy. Optical picture in color, and the pink looking thing, purple thing is the radio emission, one of the most beautiful radio galaxy image. This disk galaxy that you see is like our Milky Way. And the plasma, relativistic magnetized plasma that you see that comes out from the central region, the brachioaccretion process, that has gone very far. And this plasma blob has no atom, no molecule, nothing, no spectral line, no velocity measurement. It's only seen in radio. Okay, that way, what is interesting is things that has gone out, what it does to the galaxy when it was going out, what it does to the environment where it is blowing. You can see if this is a Milky Way galaxy, how many monster elliptical galaxy. Actually, this monster elliptical galaxy, you will have a monster at the center. That is rejecting this kind of a relativistic jet. The plasma flows out at nearly 10% speed of light. And each of them is speeding that kind of high speed in the magnetic field. They gyrate around the magnetic field and give synchrotron radiation that will be detected by VLA telescope, that will be detected by GMRT telescope. And you all will be seeing this kind of galaxies in our RGB images today. This is another picture of that. Radio is in red. Another picture, radio is in red, optical picture is optical from HST. You can see nicely stars and galaxies. What is there in blue? Blue is X-ray emission. Million-degree hot thermal plasma. This is non-thermal plasma in red, thermal plasma in blue. You can notice here very clearly that things are in different location. That means that the non-thermal plasma is pushing aside the thermal plasma. When it is going out, the shock wave is actually propagating and heating everything on the way. Okay, so that precisely is the point, that we will look at the plasma outflow from galaxies, post-merger galaxies, spot them because they will be faint and fuzzy. And once we spot them, to find out if they have affected, if they have killed the star formation process in galaxies. Because they will be faint, they will be fuzzy, we want to see in most sensitive images, we want to see the newest images, we want to see with the largest telescope in radio. And interestingly, like you can see that a red hot iron, which is looking red, is so hot. After certain 1 minute of cooling, the peak of the emission will go away from the optical band but object will be still hot, but object will be seen in infrared. Something similar, not exactly, physics is very different. But when the plasma goes out to the black hole accretion process that is seen in radio, the peak emission in the early phase, young plasma, will be in VLA band, in high frequency band. VLA telescope will be good at doing that. When it comes to old plasma, aged, old plasma, relic plasma, peak of the emission somewhat shift towards the low frequency that the GMRT is good at detecting. GMRT is a low frequency telescope. So we are actually good with our GMRT survey TGSS to spot this kind of old relativistic magnetized plasma ejected by black holes at the centers of galaxies which have gone through merger and kind of declining in their star formation. Can we find this kind of smoking gun evidence that the black hole has killed the future star formation in galaxies? And that's what we will be doing. Let me show you quickly for your imagination to help it understand properly. Jet creation process. Okay, we will not spend much time, but get the gist of this video. At the centers of this galaxy, basically, this is M87. This is the accretion disk in orange color. The plasma that is flowing out is the blue part. So this will be the radio jet that we'll be detecting. Recent news from Event Horizon Telescope is they have detected magnetic field lines. This was the 50 micro arc second, highest resolution ever possible. Tiny at the center is the accretion disk that we can't see actually, can't resolve. But the jet goes very far in a very linear, collimated, well collimated, long jets, goes several times larger than the galaxy. Okay, coming back. This will be the last video that I saw. The white lines that you see is the magnetic field. And this foggy thing that you see, smoky thing, that is the plasma that is spreading around and giving radio radiation. What happens in the weak magnetic field case and what happens in the strong magnetic field case, this has been simulations done. This is the galaxy, the magnetic field is guiding the plasma to go out. And this creates this kind of lobe. All of you will be making this kind of radio pictures and the galaxy picture. Galaxy will be seen in optical, radio picture will be seen in TGSS GMRT images as well as NVSS VLA images. And we will interpret the shape, structure, spectral index, etc. We'll understand UV-Optical-IR structure and color of the galaxies and radio images of the radio emission. You see this kind of plasma bubble, hemispherical bubble that it creates. So some galaxies where the magnetic field is weak, they will be having this kind of bubbles in spiral cases. And the large elliptical cases, this kind of strong magnetic field, well-shaped lobes, this kind of a head lobe will be forming. Okay, let's come back. We all are now knowing how to make this kind of blue, red, and green radio galaxy images. We'll spot that kind of fuzzy, faint fuzzy emissions beside the galaxies and try to connect. If you spot a faint fuzzy galaxy that is connected to a merger remnant at the center, it is possible that we will be able to discover some new cases. I think the video is still on. Sorry. This I was telling. So from the relativistic electrons, if the emission process is like this, flux density versus frequency, that will have a peak. But the plasma that is there has a different nature. This is not Maxwell-Boltzmann distribution. There are large number of low energy particles and very few high energy particles. So adding all this kind of radiation from each electron give a spectral this power law distribution, so that at low frequency from GMRT you have high flux, and at high frequency from VLA American you will have less flux. So how do you take benefit of this to detect that old plasma like things age as they become old, they start missing high frequency radiation, but they will remain in the low frequency. So things which are visible to GMRT but missing in VLA images, missing in blue image but missing in red image, maybe because the plasma is actually old, ejected from the black hole long back. Okay, so let me complete this case now. For the summary, we look at galaxies radiation, UV optical IR. We look at radio radiation in a multiple band and try to collect if the relic emission that you see in radio is the smoking gun evidence of a black hole killing the star formation process in the galaxy. And this faint and fuzzy will be best detected in lowest frequency radio telescope. And because it is faint and fuzzy, we can supply the data, large amount of data, to the citizen scientists. After training them, they can spot them and discover that kind of cases that will help the astronomers establish this model of black hole feedback behind the galaxy evolution in our cosmological history of the universe. Okay, we need to use all telescope, and we will try to understand this kind of thing. In workshop, we will get trained in the first phase, but every week, Saturday afternoon, I continue teaching in online in our Facebook group with Google Meet, and you will be continue to be trained. This is a 7-day training. You can see some of the members that will be helping us today. And then at home, then you will be part of research proposal in the GMRT telescope. For example, like when me and Chiranjeev have submitted this proposal, we got time, and all of these at home members sitting in different part and different profession, student or non-student, doesn't really matter. They are part of this research paper. And that is how you can be part of the proposal. You can be part of the paper that is published internationally. You can get recommended. You can get your PhD studentship or MSc members, MS admissions. Have got positions in US and Europe for MS and PhD. Like this, there are examples. So we all be bringing with this a picture of such members with Padma Shri Govind Swarup, who recently expired. I will end this kind of theoretical concept behind the at home, and then look for some questions. Okay. Thank you.
Thank you, sir. We'll go ahead with the questions if that's okay with everyone. Yeah.
Yes.
So the first question that we'll be asking is, someone said that can you please repeat the point of what will happen to an external environment after emission of relativistic plasma from the black hole from the center of galaxy? Okay. If the temperature in the surrounding increases, does it make that region less star forming or more star forming?
Okay, I have a picture here that to describe it precisely. Okay, this is the nearest radio galaxy where we can automatically see the maximum resolution. Okay, yeah. So this is the nearest radio galaxy, Centaurus A. The radio emission contours are here. This is an optical RGB picture. This is a UV-Optical-IR-RGB picture. Okay, so UV is showing you the star formation here.
Excuse me, sir.
Yes.
Sir, but your screen sharing is off.
Oh, sorry. I forgot about that. Can you see my screen?
Yes, sir.
So here, optical picture with radio contours. Jet is coming out from the center. Okay, here, the young star formation is happening in the UV that can be seen. The radio lobes are gone this way. What does the radio lobe does to the ambient medium can be seen here. Blue here is X-ray. Radio jet is seen in yellow. The same Centaurus, say nearest galaxy, right? So what you see is the just on the surface of the outer surface of this lobe, you can see a hemisphere like blue emission, right? This blue emission is because of X-ray emission. So the radio lobe's expansion has created a shock wave which is making the things hot to million degree, and that is giving X-ray emission. It's seen here on the bottom side. What is actually not so seen here, but you can probably guess here, and later we can see a better image, that in the direction of the jet's expansion this way, you will see a lot of young star forming blue looking blobs. So for small time, the jet expansion, the shock and outflow, etc., triggers a young star formation in that outer region. But in the longer time, that cannot sustain because the gas is also being pushed and removed. Bulk of the gas is removed. So in the long run, the small positive feedback is going to decline, and the large effect of the negative feedback that is preventing star formation will continue. I don't have a proper picture here, but you can look in the internet. M84, a nice radio galaxy close to the same M87 Virgo A. You can see that the radio lobe, wherever the radio lobe is seen, X-ray emission is not seen there, but in the surrounding region. So the thermal gas is actually vacated from that part by the non-thermal radio outflow from the jet. Okay, so we will see many examples. What happens to the galaxy? What happens to the ambient medium? That depends on various kind of physical processes. What is short-term effect? What is long-term effect? Both can be seen, because the O and B type star that is seen in ultraviolet bright blue star formation, that only lasts for few million years. But the gas that is vacated can be hundreds of million years. For that time scale, that will be vacated. That will be not filled easily. Okay. Let's have the next question.
Yes, sir. So the next question was that why don't we see relativistic jets in quasar? Sorry, he means radio jets.
No, we do see relativistic jet in quasars, but not all quasars are visible in radio. Some are radio loud, some are not radio loud. They may not be detected, but the quasar activity creates both actually. You know, the very name quasar is called quasi-stellar radio sources. So the historically, radio galaxies and quasars got clubbed historically. But now that the different technology has created so many quasars that optically there are many more, but radio-wise there are not many more. So jet will be seen in both, in some cases, not in all cases.
Okay, thank you, sir. So the next question was that how does the black hole blow away the excess gas in high luminous galaxies? Are the jets the only reason?
No, not at all. I was showing you the radiation pressure. The Hannis object, the radiation pressure is the primary reason. That is, gas is ionized and gas is blown away. Like the supernova explosion, like the stellar wind, accretion disk is so hot that the radiation pressure is creating kind of very turbulent or dynamic or driven out ionized gas there. And that is the reason also that you get the broad emission line that Chiranjeev has explained you. So the radiation pressure is always there the moment there is something is luminous. Radio jet is kind of 10% cases only it happens. Radio, all that we see is only few million year, 10 million year, maybe 100 million years, so that kind of story. But the radiation is coming from for this kind of accretion process that is visible in optical last for much longer time.
I hope that's the answer is clear. So the next question was that you said something about TV static related to the cosmic background. Could you please tell more about that?
Okay. See, the CMBR radiation, that picture that you all know, that is all you know that it is at because universe is the black body that you can think of, right? So if the black body of sun, like sun, is radiating maximally at yellow, does not mean that sun doesn't radiate in UV. Does not mean that sun doesn't radiate in infrared. We all get heat. Sun also radiates in radio. Sun also radiates in X-ray. So the black body peak may be yellow optical light, but the black body is radiating some amount in X-ray, gamma ray, till the other end in radio. Now they shift the 6000 degree peak to 3 degree Kelvin. There also you will be getting peak in radio, sub-millimeter, but there will be small, theoretically speaking, some radiation in all the radio band, all the optical UV X-ray band. Because it is already in radio, shifting from microwave to little bit of slightly 10 megahertz or 20 megahertz, slightly offset to your TV band, radiation is coming from all directions. You subtract the galaxy effect there, subtract the sun effect there. If you subtract them, TV is actually detecting CMBR. That is why there is no structure in your thing. It is tuned to TV, tune your TV channel, analog TV, old static, to any frequency. Black body is at peak, sub-millimeter, 3 degree. But there is a large range that the radiation is coming because it is a black body. It radiates in all bands theoretically. Right? I think it is okay.
Yes, sir. So the next question is, if Andromeda is going to collide with the Milky Way galaxy in some 5 billion years, then what can be said about the resulting galaxy, the Andromeda or Milkomeda, as the person said? Will the collision give rise to a new galaxy, or will it run out of fuel?
See, exact case is not possible to tell. But what is very likely going to happen is the chance of forming an elliptical galaxy is high. And because there are some hints that both the galaxies had small amount of AGN activity in the past. There are radio bubble recently discovered, a gamma ray bubble that is there. That is called Fermi bubble in our Milky Way galaxy. So the merger black hole at the center, both the black hole will merge, the gas will be removed, it can form an elliptical like galaxy, right? So there is a chance that it will form an elliptical galaxy, but exact prediction I have not followed up. The reason being that what is the gas content, what is the mass in star, what is the inclination of this object, how is the orbital parameter, all has to be considered in predicting whether angular momentum will be randomized and it will become more like a elliptical. Okay, mass are very similar, so a lot of factors are there. Exact answer I cannot be sure, but very likely in general this is going to happen. This such case happens.
Absolutely, sir. Thank you, sir. So the next question would be, a person has asked, and this question has came up like twice. So what is a halo, or what is a dark matter halo?
Okay. See, our Milky Way galaxy, you all have been reading and listening everywhere. There is like a disk as on view. And at the center, there is a sphere that is bulge at the very center. If you see this, it will be at the center. The edge on view will be the bulge at the center. But the whole sphere surrounding this disk is the halo part. What we describe is in the halo is actually there are globular clusters. globular clusters are all around in the, not on the disk, but above the disk and below the disk, you can call. Okay, so these are visible stars in the Milky Way galaxy. There are much more than this visible matter that is there. Visible disk, H1 disk, and the much bigger region is the some amount of mass that we don't really image and we don't know its structure, but from the rotation we interpret that the dark matter is covering up to the farthest radius that the H1 detection can also do kinematics. So now this is the interpretation that there is a dark matter halo in which everything is submerged, huge part. Indirectly, people have found that there is something really there, because they have seen the gravitational lensing of the background sources. And background sources, gravitational lensing or amount of bending cannot be explained with only the matter that is seen, only the mass of the visible light. You have to incorporate 10 times more mass to what is there in the dark matter halo to explain the gravitational lensing by some galaxies. Gravitational lensing of galaxies, gravitational lensing by clusters, both support there is a huge amount of dark matter mass apart from the visible mass. Next question.
So we are done with the questions. That was the last question for us. So I think we'll be moving. Ishita, can you start sharing the screen if possible?
Yes, just a second.
So should we move to the workshop or should we take a break? Sir, it's totally up to you.
Just show me the schedule once. Can you put that schedule on the screen?
Yes, sir. Just a second.
Yes. So we're supposed to be over by 1 o'clock, but it is already 1 o'clock. Right. So I think we can have the lunch break. Is that okay with organizer? Or what do you prefer? Can we pause the broadcast and do that?
Yeah. We can
Back live again after 1 hour.
Yeah.
Be louder, please.
Yeah. I'm just saying that we can have the lunch break if that's good.
Okay. Yeah,
And
we can have lunch. That hands-on session will go at 2 o'clock.
yeah, we'll start at 2 o'clock. Abhishek, can you just please pause the live stream now?
Sure, ma'am.
Yeah.
Okay. So keep a display like thing that we will start 2 o'clock or something. Okay. Now
Yes,
the
sir.
lunch break.
Absolutely.
So all the participants you can stay in the meeting, just stay muted, and then we'll continue at 2.
In the meanwhile, I would like to request that the participants who have already made their RGB images can upload in the Google form shared.
Yes.
Yeah. So those who have already made can update the Google forms, and we'll meet at 2 for further discussions. And if you're making it, you can try to submit within the half an hour first half an hour of the hands-on session next. Will that be okay, Ananda?
Yes, absolutely fine.
Yeah, okay. Yeah.
Because making is not really much difficult. We will discussion part will happen automatically. They all know the link now. Okay.
Exactly.
Okay.
Exactly.
2 o'clock.
Yeah. So we meet at 2. We'll break
2
for
o'clock.
lunch now.
Lunch, yes.
Okay.
Then we should disconnect the meeting. Hello.
Hello.
Hello, sir.
Are you ready?
Yeah, yes, sir.
Okay.
People are rejoining. We can start with this session.
Okay. See, before we can broadcast, no problem.
Yeah, Abhishek, shall we start?
Yes, ma'am. As soon as sir is ready.
Yes, I am ready.
Oh, okay, sir.
Just declare that we are starting. Then I will take over.
So you may take over. You may share your screen.
Okay. Fine. I will share the screen.
Okay, sir.
We will have our hands on. Before we start discussing, let me give kind of a demo. Demo is that how do we make RGB image analysis? What is the meaning of that RGB image? How images? What does the contour represent? We'll have a kind of all discussion first, presentation first. Then, with the help of name as listed here, we will go to each of your images and discuss and advise you further how to improve your analysis, how to interpret your images. Okay. So audio and everything is clear?
Yes, sir.
Okay, fine. So this particular part is absolutely just RGB image analysis. So you all know this part. Soon after I declare the selection list, then all these 7-day trained e-astronomers will be taking you to a Google Classroom Meet, and there you will be learning further. But even before that, let's have our nationwide RGB image analysis learning done through YouTube Live. What it is let me not repeat these things, but this one which I missed speaking in the talk, that I may be a person, but whatever you see my face in this talk, actually there are so many people on their shoulder I am actually trying to stand. It is really humbling that hundreds of people have contributed their images, their analysis, their text, their time, and their trust, and their publicity, what you see as Red Hat Home today. So all the camp committee member, Red Hat Home Discovery Camp Committee, Workshop Committee, they are organized by the same people who are my students. They have become organizer, and that is providing the service to the other people to come and learn, right? Then the e-astronomers who are going to interact with you today, they are giving you the skill training. I alone cannot do that. I have only 24 hours, I have a family to run, I have a job to do in the official for my salary, right? Then you people are coming here. You are not just learning from them. By the process of making multiple RGB images of multiple targets, you are actually contributing to Rad at Home. How? Some of the RGB images that you have made today, UV optical radio images, I had never seen them before. Some of them are so good examples of certain astronomical phenomena that I will be taking them. It is not a discovery yet, but it is a very good educational slide for others to learn from. I will show you some examples today itself. Some of your examples will be there in the screen, there in the YouTube. That is why actually when you make the RGB image, your name is interesting and the name is important. That is because you have made it. Today it is actually NGC Galaxy, well-known target. Did I get mute? No, I think.
No, sir, you're audible.
Yeah. So your contribution is already there in education of astronomy through Rad. Now, when tomorrow at the end of this day, when you will be analyzing GMRT TGSS sky survey FITS file, which are 5 degree by 5 degree FITS file. How much is 5 degree by 5 degree? Moon is actually half degree. So this way actually 10 moon and that way 10 moon, so 100 moon size. This large region of the sky you will be looking at, which has been taken by GMRT. And it is the highest sensitivity, highest angular resolution, low frequency survey. A resolution will be 25 arcsecond. You will be looking at 5 degree by 5 degree region, 100 moon size region, and you will be going to looking for some kind of faint and fuzzy sources which are not seen in other survey, not described by the published literature by scientists. So today's RGB analysis member, you will become eye astronomer after this training. You go through the training, post in the group images and accept terms and conditions and become a member in the eye astronomer group, not in the 5,000 member group, but in the smaller group. That promotion you will have soon. So point is now that, let's not repeat this thing. Yeah. So we employ all wavelength sky survey that is possible and available in the web. From radio to X-ray, whatever is there. And what are our tools? Our tools are these RGB images, right? We try to make optical RGB. The first image that you make is optical RGB. Second image on the right, IOU RGB, infrared, optical, UV. Infrared in 22 micron band, DSS to red band optical filter, which is shown in only green, and Galaxy ultraviolet image. Our India also have a ultraviolet telescope, much better resolution than Galaxy of NASA, but point is it has not created all sky survey. The telescope name that we Indian ISRO has sent, and I also use that, and a lot of astronomers use that. It has made news also several times. It's called AstroSat, astronomical satellite. So ROR image, somebody has asked what is ROR? Radio optical radio. The way you have made infrared optical UV RGB, we are also making radio optical radio RGB, where the longer band data is always put in red, and the short wavelength data is always put in blue, so that the color and meanings are mostly similar. What I mean, TGSS 150 megahertz GMRT data is put in red. NVSS VLA 1400 megahertz, 20 centimeter versus 2 meter. 1400 megahertz versus 150 megahertz. They are put in red and green. And in between, the optical data to understand where is the host galaxy which is launching this kind of plasma jets. Okay. So different surveys, different sensitivity, different resolution. TGSS, our own GMRT survey, 3 sigma, 3 times the background fluctuation, you can call it. It's roughly 15 millijansky. What maximum you put in the contour images? First contour is 3 sigma, 15 millijansky. Maximum is whatever is the maximum for that particular part of the sky. NVSS 20 centimeter survey, 3 sigma is 1.5 millijansky. This is Jansky unit, so it is millijansky. I'm saying to easily remember 1.5 millijansky maximum as in the picture. Indian data is put in red, American data is put in blue in the radio images, which we have not been posting, but we will do it. Okay, so DSS is in the middle, and infrared wide survey 22 micron is in red, and Galax in blue, GMRT is in red, VLA data in blue. GMRT is 30 antennas, 45 meter diameter dishes spread over 25 kilometers. VLA is 28 antennas, 25 meter diameter spread over 1 to 35 kilometers. Whenever they want which array, they squeeze that antennas to nearby places, or they spread it to 36 kilometers. But GMRT is always spread over 35 kilometers. Okay, so you can pi r square into n, you can think that how GMRT is 3 times bigger collecting area than VLA. That's how our collecting area is high. And in certain time, when the VLA is squeezed, our resolution is even better than VLA resolution. So this you have already used, 40 of them, 40 of you have already used it. This is very simple. What it is doing is it is getting the data from the various telescope which is submitted to NASA server. From the NASA server, it is getting your images, the FITS file original images. You cannot use JPEG file more in a more astronomical scientific way. And I have been asking you to make different RGB images. You put your name, you put the galaxy name, NGC something something, and you put the angular size of the sky that you want to look at, bigger than moon, smaller than moon area, how much you want. And you just get a PNG file, JPEG file, and you submit, and you try to understand that. Okay. Yeah, Bhushan want to ask something. Go ahead. Bhushan?
No, sir, sorry. Actually, it was by mistake.
No problem, no problem. No problem. So this RGB-maker that we have launched is actually very recent. One of the astronomer actually has created this thing, right? Avinash CK. Before that, when the marathon was launched in 2013, we were using NASA Skyview website. NASA Skyview website is also taking data from GMRT sky survey and helping the astronomers to make multi-wavelength RGB contour images and understand them, right? So that way, we need not go to Skyview in the beginning, but you will learn a lot more if you go to Skyview. Automation kills the learning part to some extent, but it gives a uniformity that I can trust and I can use your RGB images because it will be uniformly made so that I can compare what I want to see and what you have shown me, right? So RGB image is very simple. You have a red filter that allows only red wavelength to be seen, and green and blue are absorbed by the filter. Suppose you have a green filter, all the other wavelengths are, other colors are absorbed, green is only passed through. Blue is similarly the same thing. Red is absorbed, green is absorbed, blue is passed through. Like it's optical that you can understand 3 filter, you can have one in blue UV, one in infrared, and make a infrared UV optical RGB image. In optical, you call it color picture. For example, this is an optical color picture. Different color may represent different temperature. For your high temperature, it's whitish yellowish color. Low temperature, dark red, red hot iron. If you go beyond this, then you are not visible to optical, but become visible only to infrared. Stars are different color because of that. I have already described to you. It's a tool that you will learn when you become, that you can put different temperature and with displacement loss, simply you get different temperature. Let's go further. In some cases, you see extra emission in a particular color that becomes because of spectral line. For example, I will show you a spectral line picture here. This is the H-alpha emission from the whole gas cloud. Once you know this optical RGB image, you can see that red filter is showing this, red channel is showing this, but green channel, very little emission is coming here. Blue, nothing is showing. Blue, only this ultraviolet here. That is what we will do slowly. Let me, this is your Pleiades constellation, Kritika, right? This is IOU image, infrared optical UV. So you can see the UV emission, bluish emission from the stars. You can see optical emission from those sources also. But you see infrared emission 22 micron. You will also see in 12 micron, the emission from the fuzzy gaseous nebula that you see. This kind of clouds are very cold. That's why actually their peak of the emission comes around 12-22 micron. And this is same region, but radio. Radio is in contour as well as red and blue, NBSS and TGSS. What you see, you don't see the stars at all. What you see instead is not even seen in optical, not seen in infrared, but they are actually far away active black holes in galaxies very far, far away. They are looking tiny. That is what predominantly I said in the advertisement poster or emails, that you do not see stars with the best, most sensitive radio telescopes, but you see very far, far away tiny radio galaxies, because the emission process is very different. Peak of the emission is coming in optical for stars, but the peak of the emission from the gas comes in infrared. Peak of the emission from the plasma comes in radio. So they're very different process. So this is again a beautiful example of a IOU image. The gas that is compressed and pushed aside is seen in infrared. This is the interstellar medium basically. And the O and B type stars is here. Now, after some beautiful pictures, planetary nebula you can see multiple color because of multiple line. Supernova remnant you can see, right? Supernova cell, when an O and B type star explode, it has expanded in all direction. It has expanded because of the adiabatic expansion. It has cooled also, and that is why actually you can see some cooler region outer part. I will show you the next picture actually. This is why is 22 in green. So a lot of this cold stuff, 100 degree Kelvin, 200 degree Kelvin, very cold stuff, just like the backside of moon. No sunlight to heat, so it has become cool. Like the interstellar space is extremely cold. Comet, whatever is there, all the gas clouds are frozen on the solid core. That has become a comet, right? So there also, because of this adiabatic expansion, things are cooled in the supernova component cell, and that has become dust and pH-like molecules there. And this spreads all around and forms the disk around stars, and that becomes solar system. Now, why is the radio seen there then? Radio is seen because of shock acceleration, something called Fermi shock acceleration process, that the particles gain energy in the shock front and they become relativistic speed and they give synchrotron radiation. That is seen to the GMRT data, that is seen in red. What is that? That when the supernova explodes, it is propagating in the space with 1000 km per second, 1000, 2000 km per second. That is much more than the sound speed at that interstellar medium, cold, low density medium. When it is propagating at that speed faster than the sound speed or faster than the compression that can propagate to the next molecule, that is a shock. And from there, actually, particles are gaining energy and accelerating to relativistic speeds. So X-ray, radio, molecular line, optical line, various things can be seen in the supernova remnants. This is an interesting spot, a star cluster. Vela pulsar is giving this radiation pulse by pulse, phase by phase. All the accumulated emission is seen here. Spins 11 times per second, right? But the photograph that it for NVSS, sorry, the TGSS, is taken for few minutes. So all the data, all the pulses, the peaks were actually added. This is another. Here, not only the pulse is added, emission from dozen millisecond pulsar has been added and seen in radio. Stars are seen in the infrared here. This is radio infrared X-ray actually. So RGB image in the contour is just a tool. Multi-wavelength imaging is a tool. What we enjoy is what physics is there, what astronomy is there. Okay, I'm coming quickly to the galaxy case. Here is your sombrero galaxy. Dust is seen in silhouette. This is what is the RGB image, optical RGB. This is an infrared there, infrared RGB purely. It is not there in RGB-maker, but one you can also make. What is shown here? The green and red channel, not the red, rather the green channel, 12 micron, shows this dust, same dust that is seen in absorption here. Micron size, bigger than the optical wavelength, so they are all absorbed by the dust. Dust is seen in silhouette. Silhouette against the bulgeous light, optical light. Here, the UV and optical, whatever is absorbed by this dust, dust is getting heated, and that is radiating radiation in all directions. So peak of the emission is not in optical, not in UV, but it has gone down because of radiating in all directions to infrared. And you can see that in infrared, the glowing ring of dust, direct emission from dust and pH. Here in absorption, here in pure emission. Beautiful. Spiral galaxy, largest spiral galaxy. You can also make this image. Ultraviolet is in blue. Optical IOU RGB. Optical is in green. UV is in blue. Infrared is in red. What do you see? The UV bright star forming hot, massive, young stars, O and B type stars, are predominantly seen in the spiral arm. UV bright, O and B type, few million years surviving, 10,000 degree hot surface temperature, few million years surviving short-lived massive stars are in the arm. But sun-like stars with several billions of years old are in the bar and the bulge of this galaxy. And whatever UV radiation this B type stars give, that heats up the dust and pH, and that get re-emitted in the infrared. So you see in 12 micron, 22 micron. So how stellar component and ISM component, interstellar medium component, is seen in optical and IR. How hot young stars seen in UV, and primarily old star kind of thing like our sun seen in optical. So multiple components are tracked by different wavebands. That's the beauty of a color image. Here again similar IOU RGB. There are galaxies, group of galaxies, they are merging. Why some are red, some are green, some are blue? And so why some parts are not at all seen in radio, completely empty. That is because all these galaxies, now interacting, they are at a different phase of their either star formation or AGN activity. If they have a recently forming star, they will look blue. If they have recently forming star but hidden in the dust and gas, they will look infrared bright. If they have AGN, they will brighten up in the radio prominently with jets. If they have predominant star formation but no jet, then also they can show up in high frequency but not in low frequency. This is another example. This is the same galaxy that I made news, I was telling. Square kilometer area gives news, this has become my object has become an icon there for understanding star formation in AGN. I'm happy, but let's move. This is what the radio galaxy comes in. Young bright star, infrared, optical, fine, you have understood already. What is there in the contour? It is not the thermal component which either will show in UV, optical, IR, X-ray, radio, anything. It is the non-thermal component. Here you can see that the UV thing, one of this person asked this question, what does the jet do to form trigger young stars? This is forming trigger in young star formation here. You can see in blue. Later you can see in our images, you can make an image also. Okay, so sometime this jet not only is of the size of the galaxy, it goes beyond that. Right? It goes far beyond the optical stellar light, and that is what is a radio galaxy. All galaxies, for example here, all galaxies do not give strong radio emission with jets, but some galaxies give, and they become radio galaxy because of their luminosity or because of their primarily because of their radio loud size. They will be called radio loud galaxy, radio galaxy. This is a basic physical process behind that. The science talk is over. We need not go, but it was not described. So let me describe. One Jansky, the unit that we are using, is 10 raised to minus 26 watts per square meter per hertz. Very small amount, minus 26 watt. 1 watt is enough, few watt is enough to make your room light. So these are the two kind of basic radio galaxies, FR1 on the left, FR2 on the right. You will make this kind of ROR images the moment you use RGB-maker for the galaxies which are radio loud. 3C 1223, for example, this one is 3C31, this is 3C98 or something. So once I give you that kind of galaxy name, you will make this kind of radio galaxy image in a couple of clicks, right? So name of this component, this is whole thing is called lobe. This will be called hotspot. Either end, host galaxy is here, which is launching a jet. The galaxy at the center who will be launching this called host galaxy. Another one, the galaxy is launching the jet, but it is moving this way. So the plasma is pushed backward. It will be seen wide angle tail U-shaped radio galaxy, wide angle tail radio galaxy. If you rotate this galaxy around this axis, say 90 degree, this will fall on this, on top of each. So that will be looking like head tail. Host galaxy will be here moving forward. Both the tails are overlapped on one another. That will become a head tail radio galaxy. Beautiful examples, right? Like train moving and the smoke going backward. Another example is this kind of X-shaped radio galaxy. See this plasma, this old red looking tail. It's not seen to American telescope VLA in NVSS data, blue data, but it's seen only to GMRT data. That is what is old. Long before this kind of shape and this lobe ejection, there was some plasma which is still seen, still glowing in low frequency radio. Okay, so this one last example that I will give you. This is a very bright and long lobe, but there's a tiny small one that can be seen in high resolution images only. This is a very fresh plasma lobe pair ejected. And whatever was ejected before, that is diffused and spreading all around, and that has become big blobs. Okay, so finding that kind of thing when you can see a lobe, but you see the central host galaxy elongated, that is a new thing that will be speckle-like exotic galaxies that we can make news. Okay, so you can make ROR images like this. This is Speca ROR image that I made a lot of news. This is a cluster of galaxy. Same ROR image. This does not look like FR1 or FR2 galaxy. This is diffuse, fuzzy, funny looking emission. That is because all the relativistic electrons that are there in the cluster medium, they have been accelerated by mergers of clusters or because of turbulence to high energy, and it is glowing. It was fresh some time back, but today it is old enough that the blue emission is very little, red emission is very prominent. These are called relic. And GMRT is very famous for this kind of relic studies. Okay, so my kind of demo of how to interpret galaxies is over. Now we will go to all of you how to use that data, right? How to make an image and how to interpret that image. See, for example, here, let me just reload. So many people have made images. Okay. Let me go to a couple of your images. I hope I am not. Let me show this image. Manvir Lamba. Okay, this is Manvir's object. Are you listening?
Yes, sir.
Yes, sir.
Okay, do you want to say something? Did you make this? What do you understand about this? Can you unmute yourself?
Yes, sir. Sir, I observe from this image. I observe two spiral galaxies, and
yes.
the green one, I suppose, I'm guessing, is an elliptical galaxy.
Correct.
And the centers are stars. That's why the temperatures are in red. They're hot in the spiral galaxies. In the IOU image.
Okay. Okay. See, it is not because of stars actually. See, it is actually a as-on disk galaxy, right? So whatever light is emitted, for example, here it is a face-on spiral galaxy, face-on disk galaxy. So you see the ultraviolet, optical, IR light coming from the center straight towards Earth. That you can see here, infrared light is also coming from there. Now you rotate the same galaxy 90 degree and make it as-on. The disk is rotated and face-on to as-on you have turned it. Now the light coming from here has to now pass through the disk to reach Earth. That is exactly happening here. So all the light actually passing through the disks, dust and gas, and becoming less visible in optical and UV, but becoming reappearing in the infrared. That is what you see, very bright core because of dust hidden central region. On the other hand, this one has no UV emission, have no infrared emission. Why? There is no dust and pH, there is no gas there. So it is primarily in the optical band only, which is shown here in green. UV is missing, IR is missing. See the beauty. Here it is very looking similar and some information. Here much more information is available. Now comment here.
Sir, in the contour.
Yes.
Sorry, sir, I didn't understand that part.
No problem. This you see, this is not associated with any of these galaxies. It is possible that there is a far away bright galaxy or the massive galaxy which has a black hole and which is active. But that is not seen in this picture, large picture. We need to zoom in and see carefully here itself. And that may show up not in 22 or 12 micron band, but in 4 micron, 5 micron infrared. So we need to zoom in by decreasing the image size in degree and focusing on all the infrared band that we know, all the optical band that we know. We may be able to spot the host galaxies that is in the center. This is simply unresolved. If it is a background FR1 or FR2 radio galaxy or head tail radio galaxy, it is seen unresolved at this resolution. For example, this and this are both are also spiral, but this is looking green, this is looking blue and red, right? Because maybe the star from gas amount is not very high here to be absorbed. Maybe it is a small and that's why it is quickly got over the star formation process. Their star formation stage is different for this and this galaxy. So a lot of things can be discussed. And what we are doing is actually qualitatively, we are interpreting the structure and color in the image multi-wavelength. But when we do research, we need to go quantitative. Luminosity in infrared, total real luminosity properly measured in optical, properly measured in UV. We will create a color plot, UV, optical, IR, luminosity comparison. We try to fit the star formation history. We try to fit and derive the age of the stars. For example, here it is peaking in peaking in optical. UV is missing, IR is missing. So the spectrum will be different for this and this. That is what is the next more complicated and detailed steps. Enjoyed? This is your first step. We'll learn more next. Abhishek Jhala, are you there?
Yes, sir.
Okay, can you say what did you do?
Yes, sir. I chose this NGC 3007 target as per the condition that's set for choosing the target. Yeah. And particularly in ROR, I also saw that the 150 megahertz is much more concentrated than the 1.4 gigahertz. So, so I believe.
We will discuss
Okay.
that ROR.
Okay.
When we saw the picture in the Facebook group.
Okay, sir.
Here
Okay,
I have
sir.
allowed only one image to show.
Okay, sir.
So tell me something about this only.
Yes. So in optical, I see that it's more of a bluish. So I believe it can be due to hot gases or newborn star, much more population of newborn star. But here is also one thing is that there is a dark band across the edge, which is blocking in optical, and the similar type of band is also seen in IOU. So I am a little confused that how can an object can block such from infrared to UV. So what I believe is there can be different types of sizes of particle in this edge which are responsible for blocking one infrared, another type of size of particle scatters optical, third type of scatters UV. So I guess that can be one thing or no. Okay, sir.
Be a bit careful in IOU interpretation.
Okay.
The infrared is not blocked by the dust. Red is seen in the middle. Only green is blocked.
Oh yes, so it's just dust which is blocking optical, right?
So the dust is not doing anything in this picture. It is only the optical which is missing in that part. That is why the green missing, you see it as a red. If you make another image, actually, I showed you in the in my slides, the same dust lane. Okay, the same dust lane. Same dust lane is also here, right?
Yes.
That will be seen in emission if you make proper image in infrared. Okay, so this is over. So, and the contours that you see is actually not clear at this moment from this picture because of all the contours are looking circular, right? That means it is not elongated, it is not resolved. It is a jet or not, either it is a two lobe, FR1, FR2, all these details are not known because of poor resolution, blurred image. This is looking all smooth. It is possible from the star formation, supernova remnants, etc., etc. It is also possible is maybe because of small jet is there. We cannot be sure at the moment. We need to look for high sensitivity, high resolution image. Okay, let's go to somebody else's image.
Ananda.
Yes. Yes.
Can I ask something here? Can this be due to galactic winds?
See, to you, I can tell you this, that if we make a high resolution image, high sensitivity image, for example, of M82, kind of extension along the minor axis. And a lot of people claim that like magnetic flux is freezing with the plasma. The wind is actually carrying some amount of cosmic ray. And that creates a kind of a halo. So it is possible that the dust disk is clearly telling that the wind may be going in north-south direction. So the elongation that tiny is there, it is real or not, I don't know. But if it is really there, it can be related to wind, or it can related to be simply AGN jet, which is elongated. Both are possibilities there. We need to find out with the better image and spectral index information, of course.
Okay. Yeah.
If we make the image with M82, we can see this kind of outflow.
I get it. Yeah.
Okay, let's see one more image. Yes. Aman Kumar, do you want to say what is this?
Hello, sir. To me, it seems like an. Hello, am I audible?
Yes.
Yeah. To me, it seems like an spiral galaxy. The arms are quite clearly visible, and most of the light is in visible range. And the center is bright, so I guess it's a galaxy, so it can be classified as a Sifred galaxy, most probably. So I'm quite amateur. I don't know much about this, but that's what I guessed from this image.
Okay, anything about UV and IR?
Sir, I don't have any clues
Fine.
about this.
See, I can tell you, it's clearly there are very nice spiral arms, and spiral arms are supposed to be having young star formation. That is why some of them are which are at the upper part can be seen in blue, ultraviolet. But whichever spiral arm star forming region is hidden in the dust, that will show up in the infrared dust and pH emission. That's why actually arms have this dust and pH. And whenever there is UV bright star forming region, there will be a lot of O and B type star. And a few million time scale, those all O and B type star will explode in supernovae. And supernovae sizes are tiny, small. It will not be half of the galaxy size. So they are all actually mixed up, and collective emission from those supernova and star forming region, H2 region, free emission, synchrotron emission, etc., all added up and becoming this radio emission from the disk of this galaxy. Right? What is not known here, just on the picture you cannot say unless you take a spectrum. Center will always be bright, right? Because it is a center of all the stars are together there, center of the gravitational potential well. So that is not enough to say this is an AGN or not an AGN. We need to take a spectrum. Here also, center is not distinct in radio with linear structure like jet, but it's the disk of the galaxy which is having some amount of distorted irregular emission all around. So this is very likely this radio emission is because of star formation in the spiral arm. And this is an AGN or not, we need to take a spectrum from the center, like Chiranjeev explained. We need to find out whether the line widths are within 500 km per second or it is going to 5,000 km per second, so that we will call it a Cepheid galaxy. If there was a jet, we could have been very sure that this is an AGN, but it is not clear at the moment whether there is a radio jet here. This emission is from the star formation process in the disk. Okay, this is one of the source. Okay, then if there is any question at the moment, you can ask. We'll go to a different mode otherwise. Any question?
Hello, sir.
Yes.
Sir, can you please take Aman Kumar?
Okay, we'll discuss again.
Yeah, one doubt is there.
Yes. Aman Kumar subject here. Yes.
Yes, sir. Sir, in IOU image, we can see a blue patch there, right? Top
The
side.
point source or bigger one?
Small one.
Yes, this
blue
one. Yes.
patches. Yeah.
Yes.
That is maybe due to star formation.
Absolutely.
Okay.
This may be due to a compact star forming region that is brightly seen. The same spot just beside this radio contour can be spotted here.
Yeah, but there are two patches, right? One is inside contour. Yeah, why it is outside the contour? One is but there is chance for emission of radio waves due.
No, not necessarily every region will be equally bright. Okay, and the UV emission and radio emission is from different time of the star formation process mostly. When the star is bright, like sun and the Pleiades constellation, it's not giving radiation. But the moment the star explodes, shock acceleration process starts in and radio comes in after the death mostly. So there will be delay between the radio emission and the optical UV-IR emission process also. That kind of a delay is there. So not necessarily one-to-one matching is possible at the moment. But yes, that broadly this is what will be there. And also we should go to a more sensitive and low resolution image to find out radio emission is properly shaped like the disk. It is kind of irregular here because of patchiness, because of higher resolution.
Okay.
And
so,
the center part may be missing because of some thermal free absorption is happening there. We don't really know.
Ananda, I want to add something over here.
Yes,
Can
yes,
I?
go ahead.
Yeah.
Yes.
Sometimes some star formation is also seen in the outer part of the galaxies. That is because the explanation for that mostly is that because of the environmental effects, like if you have a galaxy passing nearby the galaxy in the recent few past, the gas would sometimes get compressed also rather than stripping out or tidally stripping. So the compression in the outer parts sometimes also leads to star formation in the outer disk of the galaxy, star formation burst. So you do see these kinds of things, for example, in jellyfish galaxies or in some disk galaxies, that there's a sudden burst of star formation in the outer region. So if something like this is seen here, like in the disk, I can see that outside also there are certain bright spots. I mean, in the outer portion.
See, Mamta, I agree that the tidal tail and the stripped gas can have some star formation. But, those are seen in other bands than radio continuum. Usually, radio continuum is extremely rare. And this contour that you see farther away, they are just the one contour, and we cannot be sure whether they are actually significant and real. So we need to look for, say, at least the ROR image was there. I could have said something. The low frequency, low resolution NVSS image. If that also detects separated from here, then we would start believing that this is actually something really there.
Okay.
We need to worry whether the total flux in UV-Optical-IR are consistent with radio flux here. Otherwise, it can be a background source.
Exactly.
So,
true.
Yeah. So a lot of things need to be figured out in the data first, then interpret something. Yeah.
Exactly. Yeah.
Okay. Shall we go ahead?
Yeah, sure.
Sir, I have a question.
Yes.
Why most of the AGN jets are perpendicular to the galactic plane? Is there any preference to all of these, or there can be AGN jets which is parallel to the galactic plane?
No. The statement that you said that the jets are perpendicular to the disk plane, that itself is not correct in statistical sense. What I'm saying, but your intuitive guess is that this is likely there. That temptation is there in astronomers as well. What is precisely is that the small scale radio jet in spiral galaxies has no correlation with the disk plane. It's oriented in all direction. Okay. And the second thing, the radio jet seen in elliptical galaxies are almost always orthogonal to the dust disk that is seen. So the orthogonality that theoretician or we are expecting is there in the small size scale in elliptical galaxies, but that doesn't exist in spiral galaxies. Why that is so? That is so because the spiral galaxies jets are very, very tiny time scale events. Less than few million, it can shoot out a jet and then suddenly change. So it is not lasting for a long time, but in radio galaxies, they are lasting for a long time. So the orthogonality is expected because the dust disk is supplying gas to the accretion disk, and accretion disks, the axis and the jet axis are sometimes get aligned because of Planck's theory and various kind of processes are there, that they are coupled. The spin of the black hole, jet axis, and angular momentum of the disk, accretion disk, they are all coupled. And the accretion disk and the galaxy disk coupling is not seen in spiral, but it's seen in dust disk in elliptical or early type galaxies. Okay, this temptation I also had. That's why people have studied this, and there are proper statistical studies that the orthogonality is not seen in spirals, but in elliptical with dust disks. Okay, we'll talk about the theoretical thing some other time. Anything else? No? Okay. Fine. Oh. So, kind of kind of finished this demonstrating RGB image analysis. But before that, let me also see in the group. I may have missed in the spreadsheet. It's easy to see. This is the Red at Home group where we will be joining and where we'll be analyzing all the image analysis. This is from Subham. Image could have been little zoomed in. Okay, but Biswajit has been looking at this image. Biswajit, do you have a comment on this picture?
Sir?
Yes.
Yeah, it looks like it's a lenticular galaxy, but it is way too zoomed out to accurately make any observation.
Okay.
So
Let me tell what is a lenticular galaxy.
Sorry?
What is a lenticular galaxy to the public?
So lenticular galaxy is like
what is in the spiral and elliptical?
Yeah, it is in between spiral and elliptical.
So S0 or lenticular they are called. So there is it is looking elongated,
correct,
but it is not really a spiral galaxy and not really probably an elliptical galaxy. Correct? Go ahead.
Also, this is IOU image, and what is this image? Okay, this one also.
Yeah, IOU image.
Yeah, the center looks like it is housing a lot of old stars because the green corresponds to DSS2 red, which is emitted by old stars.
Yes.
And I don't see too much of blue anywhere because it is very zoomed out.
Yeah,
maybe if we zoom in.
That is the case, yes.
Yeah.
But the nearby galaxy is having a bit more dusty star formation than the central one.
Yes, sir.
Okay. All the point sources that you see all around, some of them could be our foreground galactic star. Some of them could be background galaxies. That's why they are looking small.
Yeah.
But their colors are different because of their star formation nature could be different. Okay, this is IOU image.
Yeah, it is very zoomed out. And
one should focus on to see something more actually.
Yeah.
And yes.
Excuse me, sir. Can I ask a question?
Yes. Yes.
Sir, the
Subham,
red background we see.
Yes.
So the red background we see, is that because of noise or is that because of infrared?
Okay.
The bottom picture. The bottom.
I'm coming to that background thing. See here, the peaks has been matched to make a proper RGB image. Okay. The peak in this whole picture, whatever is the peak of the red channel data, whatever is peak of the green channel data and the blue channel data, they have been kind of normalized and matched. Then the colorful image for the bright sources has been created. But for different RMS noise, different background level, that can be different for different galaxy. So suppose the red picture is having more noise, the data is more noisy, the background sky is brighter in infrared, close to infrared, the whole background is looking, that's why reddish. Okay, this is DSS to IR, DSS to red, and DSS to blue. DSS to IR being noisy or higher background level, whole image is looking red. This is also likely the case because IR is kind of more prominent here. And further, the unit of the pixel values for UV, optical, and IR are not in the same unit. No, they are not matched. So there can be random values which are causing the background color crazy. But roughly, qualitatively, analysis is correct that these sources are bright in IR, these sources are bright in optical. These interpretations are roughly okay. Because to the same image, they are the maximized values. Relative brightness may not be in the proper unit. That's why actually we don't compare the radio and optical color, we are comparing only UV optical IR color. All of them are simply thermal. So the color, red color is cooler, blue color is hotter or younger stars. Anything else?
For now, I was only tackling the getting to understand the optical part because I wanted to go one image at a time because it is their first time.
Okay.
So
want to say something more?
This image.
Okay. Not necessarily. You can go to the other image.
Yeah. Okay.
Sir, I have a question.
Yes.
Are lenticular galaxies same as barred spirals or barred galaxies?
No. Of course not. Go to Wikipedia, Hubble's tuning fork, go to spiral galaxy or anything. The diagram the lenticular and one arm is spiral without bar, other arm is spiral with bar, right? So whenever you see a bar or a spiral arm, they're not lenticular at all. Lenticular means there is a disk component in gas or dust, but there is no. All right. Anything else?
Yeah. Also, what are the contours for? I have no background in this actually.
Yeah. Will you come into radio contours in the right images? Okay. So this picture, let's say who is commenting? Preet is commenting there. Preet, could you go ahead? Preet?
Yes, sir.
Yeah, go ahead.
First of all, the first image was not correct as per the conventions that we use at RED. Because the first image has, I guess, DSS to IR in blue and DSS to blue in the red band.
Yes.
So what convention we use is that we put higher wavelength in red normally and the lower wavelengths in blue. So that's what I pointed out. Moreover, the IOU images and other images do show some parts of the star forming regions. You can see the bright red spots.
Yes.
They show star forming regions, and the arms are all well lit by UV radiation, which means the arms are, they have high proportions of star forming, new stars, young stars, and hot stars. So that was it. I'll have to see about. No, there is no radio image, right?
There is no radio image. Yes. In the comment, I don't know.
In the comments.
No, I think he has not made a radio image yet. He has not used RGB-maker actually. At least
No,
that's why I not see whether TGS.
Yes,
That's
probably.
beautiful face on spiral, and changed. And if at all radio is detected, it individual star forming region to be having some supernova remnant, tiny supernova remnant, or diffuse emission from this region to be seen in radio. Both these things are possible. So if you go to very high resolution, very sensitive radio images of this spiral galaxy, all these arms will be having some kind of clumpy star forming region, supernova remnants. Okay, let's go to the next. Shruti KS, are you there?
Sir,
Yes, go ahead.
am I audible?
Yes. Yes, you are audible.
Okay. Sir, it's a very zoomed out image. It's a very zoomed out image.
Yes.
But I think it's a lenticular galaxy because it's between elliptical and spiral.
Okay. Okay. Anything else? No, no problem. Rohit, do you want to explain more?
Yes, sir. Actually, it is very difficult to infer upon that particular zoom level because it is just a thread sort of a structure. That is nothing much to infer upon it. So I asked her to zoom in. So, like preliminarily, I thought by looking at the RGB images or the optical RGB images, so I thought it is just a edge-on spiral type, or maybe a closely an elliptical sort of a one, slightly inclined, but the axis is slightly different one.
Okay. Okay. Let me say, this is clearly an edge-on disk galaxy. More detail are missing because of low sensitivity, low resolution, whether spiral arms are there or not. But very likely it is a lenticular. Okay, lack of spiral arm. We should zoom in. Now, there are a few more points to note here. Okay. What is the point? This is a extended resolved fuzzy source. Why I'm saying this resolved? Because point sources that you see in the sky are this tiny. Anything bigger than that is actually resolved source, well resolved source. So it is imaged properly. Here is another case. It's looking blurred, bigger, and with a cross sign. That plus sign that you see is because it is a star of our own Milky Way galaxy, very likely, not a quasar. Quasar also looks something like this. And this pattern that you see, cross pattern, is because of the arms that is holding the secondary mirror. From there, actually diffraction is happening, and this is interpreted. For example, this is 100 unit bright. Say 1% of that spills over to the diffraction spike. So 1% will be seen here. Okay, 100, 1%, 1 pixel value say 1. But this one is a 10 unit bright. Its fraction value will be 0.01. So that will not be detected because of the greenish noise here. Whatever the typical noise in this picture. That is why bright sources, their diffraction patterns are seen. In principle, everything is showing a diffraction pattern, but they are actually detected only. And diffuse things don't show that. That is how actually we figure out that they are extended galaxy. And these are either background galaxies, which are looking point on resolved, or they are nearby sources, which are stars. And the other point that is to be pointed out here is that there is a bright IR blob here. Infrared is something bright. It is probably this spot that is brightly seen is cut. So we can focus on and analyze what is this bright point coming, giving rise to. And because of this, I think the whole background is actually has become more red. And point come here. What is there at the center, whether there is a galaxy or not, unless we zoom in, you cannot show. This must be a radio galaxy which is far away. There are 10 sources seen here, so huge galaxy seen here. None of them are actually detected in TGSs, but this guy is detected. So the nature of the radiation, one peaks in optical IR, another peaks in radio. They are very faint in optical for whatever their distances are. At the center, there must be a galaxy which is bigger than this. This is small normal elliptical, so this galaxy. A giant elliptical galaxy are only hosting radio lobes. That must be very small, less than the pixel size. Okay. So this is how we actually analyze images. And once we are clear about this kind of analysis, then we can interpret the unknown sources. These are the known sources, NGC targets. We can look for them in Google or in Wikipedia. But unknown thing when you spot, you should be knowing what is the normal thing. Then we can discover what is abnormal about the new source, right? This is from Bhagyasri. Sorry, I cannot pronounce it. Are you there?
Yes, sir. Am I audible?
Go ahead.
Okay. I could see the spiral galaxy, and
Besides it, there is a star, I think, and they are in the optical range. And also at the bottom of the image, I could see contours.
Yeah.
And yeah.
Okay, you have more images, I guess. You zoomed in, is it, or different target? Zoomed in. Yes, go ahead.
Yeah, sir. I don't know that much about it.
No problem. You are just learning. I want to see how much you have guessed, how much you have learned, how much you are interested in, and then we will proceed from there. Now, who is commenting? Asutosh. Do you want to say? Asutosh, are you there?
Yes, sir.
Okay, go ahead.
So there is also another galaxy near it that she is
This
pointing.
one?
She is missing that. I asked about it.
So you can
And
yeah, go ahead.
and can the all those sources like the at the bottom
Yeah.
and those two galaxies, can those be connected or something like that?
Okay.
They are emitting radio, so
Yeah. So something you all know clearly, this is like a lenticular, this is extremely long and thin disk. Okay. What is interesting here is that this has become brightened up in infrared. Let's look at the same thing, whatever we have been discussing is UV-Optical-IR. Let's come to this picture. It is a radio image. Same target, everything is same. Whether the optical is seen over here in green, right? This one is this guy, this is this one, everything is 1-to-1 match, this is elongated. But this picture does not show TGSS radio contour. It shows only NVSS radio contour. Correct? Left bottom is TGSS radio contour. It is written here, red ROR, RGB ROR with TGSS contour on this with NVSS contour. 1400 megahertz image detects it, but 150 megahertz image does not detect it. Why Indian telescope did not detect, but the American telescope detected? There can be multiple reasons. One of the reasons I said that the radio emission which is bright in high frequency, maybe because the plasma there is young, right? If it has become old relativistic plasma, GMRT picks up. But before we interpret that science, we need to be a bit more careful. What is the noise in this picture that above which is called detected? Noise here is 15 millijansky. And noise in this picture is 0.5 millijansky. So that is why this is actually a sensitive image, more sensitive image. And furthermore, it is also possible that the spectrum of this galaxy in radio can be different. If it is a flat, maybe related to star formation process, free emission process, so you detect it, then that flat emission will not give much radiation in the 150 megahertz. This is first contour is 1.5 millijansky. Here the first contour would have been 15 millijansky. So sensitivity difference could be the cause, or spectral index could be the cause, or the nature of the spectrum. So now from this RGB picture, ROR picture, we need to go to further more quantitative analysis, that how much is the measured flux in this region, that the catalog has already automatically calculated. You can note my words, that sky has been imaged, sky has been measured, but not everything in the sky has been discovered. Sky has been imaged, sky has been measured, but not everything in the sky has been discovered. What I mean, automated catalogs, optical, UV, IR, radio, everything, they do all sky survey. They measure every position, brightness of every detected sources above 5 sigma or 7 sigma. But what is that source? Automated algorithm can only tell the quantitative values. It cannot tell the quality of that source. Here we are interpreting the quality of the source based on our various physical, astronomical understanding or knowledge. Here comes the role of trained citizen scientist. That's what I have been saying. That you have been trained to interpret the data. Heterogeneous, multi-wavelength, multi-parameter, different data, different telescope. But once we combine them, we have a brain, we have astronomical knowledge to interpret that. And that's what discover. That's what in 2011 when we discovered SPECA, the data was there in NVSS decades ago. Data was there in DSS decades ago. But nobody had discovered. It is not that nobody had published something on that paper, on that object. The radio image, the optical image were published. But nobody connected the radio and the optical picture to make the discovery that this is an exotic galaxy. Nobody has seen that before, never seen before properties. First such episodic spiral host radio galaxy. So that is the point, that you need to be trained. Although the data is there in the sky, nobody knows what the telescope has found unless a human scientist looks at them. Okay.
Sir?
Yes.
Sir, can you just reopen that last NVSS TGSS ROR image?
Yes. Yes.
Yes, sir. In this NVSS image, we see contours, and especially as we go further out, the contours are elongated at the bottom side. Can we interpret it as a release of gases, or it can be due to some noise fluctuations and stuff?
So not at the moment. Not the moment. There is something called actually what is the reliability level of this blob? Whether this is really there. For example, this is actually drawing the blue emission, right? NVSS is in blue. So, but blue pixels are everywhere there, right? Why did not draw everywhere? Maybe the contours are just starting here 3 sigma level, and by time you reach 6 sigma, elongation is gone. Okay, so the reliability level is quite low. At the same time, this is not really an independent source probably. There's just a fluctuation in the outermost contour. So we need to go to another wavelength. You need to go to a deeper way. You need to be careful about how much noise you are estimating here is true or not. Because everywhere we have put a uniform knowledge, uniform RMS. You need to look at carefully by looking at the data, not just from this image. Okay, your guess is right. We should be thinking that is there something elongated? Yes, we should be thinking, but carefully first verify the data is saying that. Then comes the interpretation of the science. We should not be saying wrong statement. So our science can become wrong in the future paper, but our data should not become wrong in the current paper. All right, okay, let's go.
Sir, in this ROR with NVSS, what is the difference between NVSS blue and NVSS contour?
No, the NVSS is always put in blue.
And so the contour is also due to the NVSS.
Same.
So both are representing the same wavelength.
The point is that, see, for example, here, both are representing the same data.
Okay.
In radio, the sky is actually much more noisy compared to the optical picture. That is why actually here I am not drawing contour, because easily one can distinguish which is a background star and which is the galaxy that are of our interest. But our radio images are always outside the optical galaxy, are in diffuse and faint. That is why whether the diffuse faint emission is statistically significant, we need to draw contour quantitatively to figure out whether this is real. So that is why it is compulsory to have a radio contour. For example, here you can see red emission is everywhere there, but there is no TGSS emission actually from the galaxy or anything significant. Only the NVSS emission is detected significantly.
Okay.
Okay, let's move on. Ninisa Manaswini. Sorry. Are you there?
Yes, sir.
Okay. You want to say something?
Yes, sir. First one is the image of WISE 3.4 in red channel, and DSS to red in green channel, and in blue galaxy near UV. So from WISE 3.4, generally the hot stars emit IR in this region, in this range WISE 3.4. So, sir, the pink arms, the pink region in spiral arms are due to this, and the outer blue region is due to the galaxy near UV, which shows some presence of some young stars or old stellar population. And as we move into the central bulge, it is showing yellow means there is the presence of both DSS2 red. Yes, sir. DSS2 red and WISE 3.4 means there is the presence of old stars here.
Okay. This is roughly the same,
yes,
except that 20.
Yes, sir. 22, WISE 22, which is due to the presence of dust.
Yeah.
In the star forming region.
These UV bright regions are emitting UV light,
yes,
but if you equate, that energy has become more than 13.6 electron volt, which can ionize the surrounding hydrogen.
yes,
O and B type stars emit maximum radiation. Surface temperature is so high that the peak of the emission is UV. That means 14.6 electron volt and above. That can ionize the hydrogen, and that is going to create a ionized star H2 region surrounding that. But that photon is getting absorbed by the surrounding dust. Now the UV photon could not come out, but it is getting re-emitted in the infrared. That is actually this star forming and backward to the 22 micron emission blobs. This is probably you have put a red, I think, not so prominent. But the point is not hot stars actually, rather they are old stars, or they are surrounded with so much of gas and dust that they are not seen in optical, but primarily seen in the infrared, 3.6 micron. It is not 22 micron. Okay,
yes,
22 micron will be diffuse and because of the dust.
Okay, sir.
Anybody who has commented on this? Oh, so many comments. I didn't notice that part. Vishwajit, do you want to add anything that I said?
Yes, sir. Basically, if you look at the first thing that stands out is the image 3 filter order is not conforming to our group standard. It has been reversed.
Yeah.
So because of that, the TGSS is in blue and UV is in red, because of which the third image looks very different. If you if you click on see more in the description, it is listed.
Okay. So I was suspecting this is NVSS, but it's actually TGSS in blue. I see.
Yes, sir. So that is why you see all those spots. Red is supposed to be UV, which is why it is showing up in yellow because of the arms having star forming regions.
Yeah, I did not comment that part. That's why I got confused.
Yes.
Anyway, that's the point. Basically, you follow a particular protocol that the moment you see the color, you interpret the physics out of it. Don't flip that ordering. Follow the rule.
Yes.
Always long wavelength in red color and shortest wavelength in blue color. Okay?
Yes, sir. Yes,
and
sir.
to avoid this kind of confusion, we had to make this RGB-maker.
Yes, sir.
Okay, anyway, so you will comment and you will learn.
But other than that, also you can see that the galaxy has a very interesting shape by itself. If you look at the galaxy itself, the arms are bent in some area and elongated more in some other
not
space.
Uniform. This kind of compressed kind of thing. It just looks straight.
Correct. So if we zoom out, maybe
zoom out, or maybe we should look at the H1 image of this.
Yes, sir.
That will show up some kind of kinematically disturbed structure. Maybe Mamta can comment.
Ananda, this probably is due to some nearby galaxy passing.
Probably.
So on the bottom left, it's compression. The gas would be compressed from that side if you see the H1 image. That's my expectation.
Yes. That is also
left half and right half are not symmetric, basically.
Exactly. Or there is some kind of tidal stripping that is happening. Rather than compression,
possible.
There's a stripping that is happening from the top right.
But if there was stripping, oh, okay, that explains the diffuse star formation to the top, right?
Yes.
Okay.
Yeah.
We'll have a large scale picture of this.
Yeah. So you need a little
Extreme,
zoomed out picture of this so that you know the nearby sources.
Correct.
Yeah.
These are
so
all
in
NGC targets. So one
Yeah.
can look literature also. It will be there
Yeah.
already in the literature.
Exactly.
But we are doing net practice here, basically, so to learn these things.
Yeah.
So basically, we were discussing about how dust will absorb the energy from the high energy young stars and then show up the radiation in the IR spectrum.
Yes.
But
okay.
Yes, sir.
Okay. Let's move on. Nobody has put a radio galaxy so far. Okay, we can. Jisant Talwar.
Hello, sir.
Okay, go ahead.
Sir, I have shared the zoomed in image in the comments.
Okay. Let's see that.
I think I have replied to Preet, sir.
Yeah, here is the zoom in image,
yes,
right? Okay. Okay, good. Go ahead.
So, sir, here we can see a spiral galaxy at the center, and there is a bright, massive object at the center of the galaxy, which could be a prominent supermassive black hole. And also towards the bottom right of the image, we can see a contour, which may be because of some far massive source like a black hole or any other thing, which could be observed when we zoom in more or the image is better resolved. And in the infrared part, we can see that the blue regions in the spiral arms because of the young star formation in the spiral arms, and near the center, we see the infrared part is more prominent because of the old stars present. And sir, I have a doubt, like in the optical image, we can see there are two spots also other than the center.
Yes.
So I'm confused, like, are they in the galaxy or they are coming in the line of sight?
I was about to comment that. Now, suppose those 2 point sources, I can point out here and here, just about to be on the disk. Suppose it was some kind of star forming region in the spiral arms. Then that should have shown up either in the UV or in the IR. Right? It may or may not be showing up here. May be showing up simply because the 22 micron is actually having poor resolution.
Okay,
so even if it is showing up, the infrared image itself is poor in resolution. That is a blurred image. So we are not very sure whether those two regions are showing up in the 22 micron image. But what is clear is that these two regions are not showing in the ultraviolet. DSS picture is 2-3 arcsecond resolution, but Galaxy picture is 5 arcsecond resolution. So very likely these two sources does not belong to the galaxy. Could be background galaxy, but actually if it was background galaxy, then it should have been reddened by the dust and thing. So this is very likely something of our own Milky Way galaxy in the foreground.
Yes, sir.
Likely. These things are actually, with limited data, whatever science can be suspected, can be interpreted speculatively. We need to have a lot more quantitative data to say that.
Okay, sir.
Okay. And you have already said this, so nice. Next we come to the same galaxies, ROR images. Can you say?
Sir, I'm quite new, but I can try.
No problem. No problem. That is what we are trying to know. Optical UV-IR interpretation is relatively easy. Stars people really understand, and we will be understanding what GMRT does, which doesn't talk about star, right? It talks about something else. That is why actually we need to grow from that star formation understanding to AGNs and radio galaxy and diffuse emission in the cosmology clusters, etc. Okay, so I think Preet has been commenting here, right? Okay, Preet, do you want to say something?
Yes, apart from what all we have discussed already, one thing that we probably hasn't been pointed out yet is that the TGSS and NVSS contours look different. Like TGSS contours are more compact and NVSS contours are more spread out.
Correct.
So that we can explain by resolution. Like we know that NVSS has a resolution of 45 arc seconds, while TGSS has a resolution of 25 arc seconds. So so that TGSS has more resolved images.
Hello.
Hello.
After resolution 45, whatever you said.
Am I audible or?
You are, sir, is cutting out.
Okay, I think sir's network is. Hello, sir.
I can hear you.
Yeah. Okay. So that I was saying that we
Just
know
repeat.
that. Yes. So NVSS, we know that the resolution of NVSS images is about 45 arc seconds. That is the smallest distance that NVSS can resolve is 45 arc seconds, while that of TGSS is of 25 arc seconds. So that is why we see this concentrated contours in TGSS, because NVSS shows a bit bigger pixels because it cannot resolve smaller sources. So that's what we haven't discussed yet.
So I had one question, like in NVSS, as you said, the resolution is less as compared to TGSS. So, so we can see that the contour is like compact in TGSS. So, so like TGSS is actually looking farther with proper resolution. So why is the contour like on the left in that we see in NVSS appears and it is not in the case of TGSS?
That has already been discussed. Actually, sir already said in the previous post or something that the sensitivity for NVSS is 1.5 millijansky, while that of TGSS is 15 millijansky. That's a difference of like 10 times. NVSS can detect up to 10 times fainter sources than TGSS.
Okay.
That is why that extra contour comes from.
Okay.
Okay.
Thank you. Thank you.
Am I audible?
Yes, sir.
Okay. So sensitivity is one issue when you compare this thing in the same resolution, same frequency. Here the images are actually in two different frequency. Okay. So one is 150 megahertz, another one is 1400 megahertz, roughly 10 times different in frequency also.
Yes,
so if you take a spectral index of -1, whatever is 1.5 millijansky in NVSS, say this tiny contour here, say this is 1.5 millijansky source in NVSS. With a spectral index of -1 at a frequency 10 times lower, the flux would have risen times, which would have become 15 millijansky. 1.5 in NVSS would become 15 millijansky in TGSS. But 15 millijansky I should have detected it, but it is not. That means this source, if it is real, it would be actually a flatter than -1 spectral index. So very likely that this one is also the same thing, that this is flatter spectral index. Then this is a radio galaxy, very likely that's why it is steep spectrum and this is seen in both. But this one, why this is not detected here is likely because the spectral index is flat. And flat means likely because it is not only having synchrotron radiation from the supernova remnant, but also having good fraction of free radiation from the star forming region. That's why this spectral index is flat. Flatter spectral index means less bright compared to expected 15 millijansky. That is why actually this guy is actually not detected in TGSS. So that is what I was saying again, that this sources NVSS may be good at detecting sensitive young plasma, but we are good at detecting old relativistic plasma in slightly better resolution. So if it was actually old plasma, steep plasma, we could have detected it, right? Usually,
Yes, sir.
typically the normal thing are 0.8 spectral index, not -1. -1, we would have detected it. That's why I'm saying TGSS or GMRT is best, highest resolution, highest sensitivity, lowest frequency sky survey to detect old relativistic magnetized plasma. We are kind of good archaeologists as far as black hole activity is concerned.
Got it, sir.
Okay.
Thank you.
Is that done?
Yes, sir.
No, okay. Let's see. Any other question other than this kind of thing? Anybody else? We will see Varun's object
Hello.
also. Yes.
I have one question.
Yes, go ahead. Who is this?
Like
Say your
if we
name.
have to detect the black hole in any galaxy.
Yes.
Sir, I'm Shubham Srivastava, sir.
Okay.
Sir, I was asking like if we have to detect any black hole, then what kind of filter we use? We use gamma ray, or sorry, gamma filter or some other.
Hello.
You got muted.
Hello, sir, I was asking like if we have to identify or detect any black hole, then we have to use a gamma filter or some other sky survey. Like I have used a Fermi 5, the first image which you was discussing. In that, firstly, I was sure that it may be a black hole, but the same image, if I have used in a gamma filter, then there is no object detected. So I get confused that it may be a black hole or not. That's why I was asking like how to identify any black hole, that it may be possible in a center of a black in a center of a galaxy.
What do you mean by gamma filter?
Sir, I have checked the NASA Skyview survey. There they have mentioned that to identify the center of center of the any galaxy, if it is a black hole, then we use gamma filter like Fermi 5, Fermi 4, Fermi 3. These kind of filter we use.
Okay. Got it. See, the point is whatever RGB image task that I am giving, I am not including many X-ray and many gamma ray images, and many radio images also I am not including. The primary reason behind this is twofold. One is technical, one is actually political. The technical thing is that there are very few all sky survey with good sensitivity and resolution. Combining these two aspects, WISE, GALAX, DSS, TGSS, NVSS, these are almost all sky it has covered with good resolution and good sensitivity. Okay, so that is why when I'm giving NGC this, NGC that, it has to be covering most of the sky. Then otherwise, actually, half of the people will be, no, sir, I don't have data. No, sir, I don't have data. We are not doing that. Once you detect something interesting, we will then look for all the available data in Skyview or anywhere else. Okay, so the political aspect is, when we launched Rad at Home Citizen Science, and even today, there is no citizen science program in India which is using or which is involving Indian telescope data. Neither they are discovering from Indian data, nor they are training the citizen scientists from Indian institutions. You search in Google, citizen science astronomy, India. Hardly you will find anything other than Rad at Home pages. Okay, so that is why my focus is always, if you are interested in black hole, there are X-ray, optical, IR, gamma ray, all band has some ways of detecting where the black hole is active. Because by definition, any activity more than star formation process is assigned to black hole activity accretion process. right? Almost all X-ray astronomer, half of the radio astronomer, all work in AGN. So the point coming back that unless you quantitatively compare the X-ray fluxes, radio fluxes, gamma ray fluxes, you cannot be sure whether that has a black hole just because there is some gamma ray emission. But very likely when you have high energy emission at the center, it is likely due to black hole. But the black hole bright in gamma ray not necessarily will be bright in TGSS. You cannot have a spectral index that will stretch from radio to gamma ray so that you can predict gamma ray detected, radio detected, gamma ray detected, definite. No such thing like that. So that is why we need to answer your question of black holes presence from RGB images based on case-to-case basis and based on quantitative analysis. We are slowly learning. Let's first focus on understanding the basic galaxies in UV-Optical-IR, then understand radio bright galaxies from ROR. Next, once you discover something, then we will go to analyze it, observe with various telescopes, and whatever data is available in the internet, or we will ask for data. Like TGSS discoveries, we have got 50 hours of 60 hours of data from GMRT. We have observed it. TGS has looked at this part of the sky for only 3-4 minutes. And when we go and observe with GMRT, with the ongoing project called GMRT Observation of Objects Discovered by Astronomy Collaboratory, GoodRAC, there will be observing that part of the sky for not 5 minutes, 5 hours. Now you can think of how much sensitivity increase it will be making. The sensitivity increases or the RMS noise decreases by 1 upon square root of time. So for 1 minute, if TGS is observed, if we look at the same part of the sky for 10 minutes, then square root of 10 times the RMS noise will go down. 3 times low the RMS noise. Instead of 15 milliansky RMS noise, in our 10-minute observation, the RMS noise will become 5 milliansky. Instead of 15 milliansky, the first contour will come to 5 milliansky. So that is what I kind of lost the scientific aim. So let's focus on understanding the activity at the center first, star formation or black hole related. Then we'll connect whether what the gamma ray says it. Okay, I'm not also a gamma ray astronomer. I cannot comment much what the Fermi people are doing. Okay.
Okay. Thank you, sir. Thank you so much.
Okay. So I don't know what plan I had. I forgot. But Varun, are you there?
Yes, sir. I'm here.
Yeah. Say, what do you understand?
Hello.
Yeah. Go ahead.
Yeah. So, hello. Good afternoon, sir. My name is Varenya Kumar Dev, and I targeted this NGC 1012 galaxy. It is a lenticular galaxy in Aries constellation. I looked it up, and we can see the RGB IOU image that the galaxy is completely green, indicating that the stars are likely to be old, but you can see a very faint reddish orangish glow in the center. And in the second picture, we can see a faint stripped blue like structure in the top left corner. If you can see, I don't know what to make out of it because I'm completely new to this. And as we can see, the final NVSS image has a larger contour because of what I came to know from this lecture, that is very sensitive to radio waves than TVSS. So that is detecting probably the younger plasma, and TVSS is detecting the older plasma. So contour in the last image is greater than that of the other three.
Okay. Is there anybody who is helping you in this analysis?
Me, sir.
Yeah, Vishwajit.
I think Vishwajit sir was.
Okay. Go ahead, Vishwajit, if you want to comment something.
Yeah. First of all, the thing that stands out the most is the shape of the galaxy. It seems to be bent on the bottom part.
Yes.
So that is interesting. But also, if we look at the optical part, what is interesting to me is that there's a lot of blue in the RGB image.
Yes.
But it is not enough that it shows up in the IOU image, the ultraviolet side.
Correct.
So I'm interested in what is going on there.
Anybody else has a comment on why it is that?
I think that Galax hasn't covered that part because the patch is ending.
Yes. Correct, Akshat. See, the blue confusion that he is having is, see the top, that corner is actually the Galax data.
Yeah.
This galaxies fall exactly at the edge of the detection.
Yes, sir.
Unlucky galaxy. Okay.
But also the radio contours seem to be bent similarly.
Yeah.
So it looks like it is because of the movement of the galaxy. The TGSS data has also is showing a slight change. But there's only one lobe.
Any other astronomer exam for you now? Anybody else has any comment?
Yes, sir. It is like you can actually see there is something like a blobby thing in the arms. Blobby things in the arms. I think like I would like to focus upon that and look whether it is having any supernova or any other things that had happened in it. Blobby things in that, like it is not even linking it because it is straightly, it is in optical, that too in red. So I think I would like to focus upon that particular thing. So to confirm upon the radio contours, if at all possible.
Yeah, you're right. Anybody else? Akshat or somebody? It's a
Yes,
puzzle.
sir.
Yes.
At first, it seems most of the radio emission is due to stellar events.
Correct.
Like we see those supernovas or those kind of bright events happening in the disk of the galaxy. Yeah, probably I suspect that the radio emission is due to the stellar events.
And
but
also,
we will
sir,
need
continue.
yeah, but we'll need higher resolution data to figure out really those are, because the TGS's data is not covering the lower part where Rohit was probably saying that we see those blob kind of things. So that's also interesting. So we'll need like higher resolution data to like confirm something.
Yeah, I agree. See, the elongation of the optical emission, roughly inclined north-south, that same elongation is there in the NVSS. So the NVSS image is resolved and the alignment between optical emission and radio emission in 1400 is true. So the disk emission seen in radio is there. It is related to star formation process. Okay. But the TGSS emission is not exactly aligned, neither at the center exactly. It's kind of inclined thing, slightly offset from the orientation. So what I'm not sure is whether the beam of the TGSS in that part is really like that, or there is something jet-like thing or something else. We need to be a bit more careful. It's kind of a puzzling to me. What is that extra elongation
Ananda,
or deviation?
Can I add something?
Yes, go ahead.
There is a possibility of a warp at the end of the galaxy in this case.
True, but that is not matching with the radio, right?
Yeah, I mean, I was just looking at the next two images, and from there's a possibility of a warp from the optical and the contour alignment.
Possible. You can see the curved disk basically.
Yes.
But my suspicion will be actually it is kind of a irregular ram pressure stripped galaxy.
But then can you go to the next image, please, which you were showing the So, but then in that case, there would be elongation quite, see, these contours in the right image are quite symmetrical along the elongation.
But
So
it
if
is
that's
too
a
poor
ramp
in
pressure,
resolution.
huh.
Too poor in resolution.
Yeah, exact. I agree with that. So for the ramp pressure stripping thing to be happening, there has to be a lopsidedness present in this.
Not clear. It is puzzling to me so far, actually.
Yeah, I mean,
Excuse me, sir. Sir, I have uploaded 2 images.
You have uploaded 2 more
Hello.
images.
I have uploaded 2 more images from NASA's Skyview. I have uploaded one DSS-2 infrared in comment section. Kindly check Vishwajit sir's reply. It has a better contour, I guess. You might check.
This is just
IR contour.
poor resolution.
But this is IR.
Hmm.
That will anyway not show if anything star formation effect is happening.
Correct. But also the ramp pressure seems to be influencing the bottom part of the optical in the optical images.
Which wavelength was this, the last image?
The last one is out of order.
This one?
Ulta, but IR is
blue.
It does not basically show up any kind of
I guess there is not much effect of ramp pressure stripping in it, because this has to be, if it is ramp pressure, then and you see star formation happening in the ramp pressure strip tail, there has to be quite a lot of ramp pressure stripping happening towards that end, and then the asymmetry would be much larger. As
can somebody check whether far UV data is there?
Let me do that.
Yeah, NUV it has missed little bit. If the pointing is slightly offset in another run, then it might be cut in the far UV data. I think it is an NGC galaxy. One should simply go to literature. It is very confusing otherwise. I hope the TGS's elongation is actually correct.
Sir, what should be the correct order of RGB?
No, 10 times we are describing, right? The longest wavelength should be put in red. The shortest wavelength of data should be put in blue, as long as it is UV-Optical-IR-RGB. If it is radio-optical radio RGB, then the long radio in red and short radio in blue. In between is the optical. Okay, while somebody is checking, let's finish quickly couple of images only. I think we are done. This will be the last case, I think.
Far UV does not have data, sir.
Okay.
Would you like to try in an SDSS, sir? Like SDSS has a good amount of
check. Go ahead. This is NGC target. Wherever it is, we'll solve it.
So actually, I recently checked it on NAD. So it isn't giving any information about it in the UV band. Like there's information about it in X-ray, visible, near IR and far IR. Like in NAD.
Let's check in the data first, because they're checking SDSS. If SDSS is there, we can easily solve it. Okay. Now this is Bandhan yes. Goyal. Okay. What did you do?
So this is NGC 3001. So first one is optical, and so in the IOU, so we can see nothing is in UV, and and also there is not much infrared. A little bit yellow is there, so I think it is near infrared.
Yes.
And so like and based on the contours, so it is not symmetrical. Some concavity is there on the towards the top right. So I don't know the reason why is that.
What can you say about the radio emission? Do you have the NVSS image? Okay, the bottom. Yes. I'm showing you the NVSS. Okay.
Yeah. So so the spread in NVSS is bigger than the TGSS, and then we can see that both TGSS and NVSS are getting some data. This is not as particularly. So I have one doubt here. Okay, so that's due to the resolution. So it is just the concavity that is a little something that can be thought upon, but otherwise it doesn't seem anything interesting.
Okay. Anybody else has comment? Who of the RAD members commenting? There's two. Who wants to go? Nobody finding it difficult? Okay.
Sir?
You already know. Sorry.
Were you saying something? I was looking at the other data.
Yes, you want to comment on this object?
This looks like.
Okay, fine. Let
it's a
me
spiral.
see.
I
It's a
think,
very
sir,
nice
it is
spiral,
like,
right? The bar
I
spiral.
think it is. I think like it is whatever radio data it is very pointing out to us, like at that sort of a thing. It is slightly matching that center, both of them.
Okay, the rough north-south elongation is truly there both in NVSS and TGSS. Okay, and the squeezing at the center, the neck-like thing at the center, is likely real. It's a bit funny, but likely it is real. And that is not very surprising because bars are usually made up of older stars. And the way this galaxy's inclination and bar are oriented, that the northern half is spiral arms, southern half is other spiral arms. So the radio emission from the north and south kind of getting slightly resolved out, two separated, because old star is in the middle, right? This is the red part. So likely this is simple star formation from the disk. What I'm not sure is whether this has a AGN that is north-south elongated. And we are not detecting that because it is poor resolution. What is clear is radiation mostly coming from star formation. What is clear is the middle kink is likely due to the older star of the bar. The star formation in the northern half is in the spiral arm of the north side, spiral arms of the south side. So we should have a spectral index information. We should have higher resolution picture to figure out whether there is a AGN or not. Okay, but this kink is because of higher resolution. This is interesting.
Sir, am I audible?
Yes.
Sir, since we are looking at this galaxy of face on,
yes.
is it not possible that it's having lobes, but we will not be able to see the lobes because we are looking at them? They are in our line of sight.
No, true that spiral galaxies usually don't have this kind of large lobes. First of all, Specais and exotic example cases, only 6 such known. Second point is that this is so nearby object that this is not made any news of big blobs of lobes like thing. So this is very likely star formation with a Seyfert with a jet-like thing. So we should look at the literature first and then interpret furthermore. So lobe interpretation is not correct here simply because of this, that large scale lobes are not there in spiral galaxies. But
okay.
Small amount of AGN can be there, small amount of bubble-like thing can be created there. Morning I showed you the weak magnetic field lobes and the strong magnetic field lobes, the simulation images. This can be the weak case and bubble-like thing can be there.
Okay.
Let's go to the last one, I guess. And after this, we don't have any more. Done. This will be the last. Bandhan.
Yeah.
Your second object.
Yes. So this is NGC 7001. So I have also posted a zoomed out picture in the comments, and there is also a very zoomed out version in the fifth and sixth image, the next one. So in this picture, the fourth one, we can see the contour is a little offset towards the left.
Yes.
The previous one. Yeah. So we can see a contour is little offset towards the left. So we were discussing in the comments. So I think Vishwajit or Preet was there. So they said that we have to look at some other data so that we can like conclude that whether it is from. It seems like it is from a different source.
Anyway, comment something on this.
And here, so we can see some red blobs are red objects are there. So that is observed by the TGSS, and nothing, like there is very little detection from the NVSS, and it is just optical.
The red source there at the bottom, the
Yeah.
strawberry is interesting.
Yeah.
We'll talk about more when we compare radio-optical radio, but that the asymmetry that you have spotted, we need to check out in the infrared. Instead of red will be in the infrared, and radio contours can be kept there.
So I had one question. So in the zoomed out picture here, so how can I know the name of these two objects? The red one.
This is the next one you will learn, that it is you are looking at the RGB images of named galaxies, and this is something, right? So when we'll be given in the next session the large FITS file, and you find some crazy source, there how do you search whether that source has been published by scientists or not? So there actually we go by finding out the coordinate of the galaxy, search in a NASA extragalactic database. It connects the galaxy name, galaxy coordinate, database, and publications.
So I tried that. So like, is it I have to do that? I have to just overlay the images, and then I have to see that which coordinates correspond to that particular places.
No, RGB images will not provide you that. You need to look for the coordinate of individual sources in a separate data.
Okay.
Okay, RGB image doesn't provide you that. Okay, so instead of putting this image, we could have put the WISE channel 1 or channel 2 in red, and say optical picture is already there, and blue can be something else. Not poor resolution, but we are looking for whether there is a associated optical galaxy to this.
Okay.
Oh, this is seen in NVSS only. I think this should be checked with another NBAS data. This should be easy to interpret. I guess it is connected. It's very low signal to noise ratio. Maximum could be very low. You have put so many contours just by default, but maximum could be low. This is just offset, and NBS has detected emission from this galaxy. It's not from some other galaxy. My feeling is that.
So is it because of like the code, how it is plotting the contours, or it is like the contours exist at that particular place?
No, it is nobody's fault. It is not code fault or something. It is that we are just seeing the tip of the iceberg.
Okay.
So we just spotted the peak. We need to go a little deeper and see how it is connected with the nearby galaxy, basically this particular one. Once we see that connection, then we can become easily sure that this belongs to this. We are not seeing the connection because we have seen only the tip.
Okay.
We should just go to sensitive image and find out. Okay, I think we have finished our interactive session, and I hope some of you have already learned how to make such images and discuss. Let's let me coordinators, let's have some other person who has not made an image but wants to ask some questions related to RGB image or related to something else. Then we will kind of decouple from the live views.
Sir, I got only one question during the session.
Okay.
That was that is it a limitation that we can't take 8 XYZ or above that in the maker?
Sorry, say again.
Is this a limitation that we can't take 8 XYZ or above that? I think she was referring to the RGB-maker. Sridevi, are you here? She asked this question.
Hello, sir.
Yeah, you were asking. So ask again. I didn't get you.
Sir, I'm not sure whether it is a blunder or not. I'm just asking, you gave us opportunity to take a pin code protocol.
Yes, yes.
So take last three numbers and you can add 1, 2, 1, 2, 3, up to 7. Huh?
Okay.
So I didn't get 8, adding 8 or 9. So is it a limitation or something?
Yeah. Got it. And now it's a good question. There is some logic why I have put that rule. See, the number of galaxies in NGC catalog goes something up to 7,000. It doesn't cross 8,000 something, 9,000 something. Okay, so that's why I asked you to put I could have asked you to put 4 last numbers of your pin, but then you will confuse that why 8,009 something is not giving you a result. So that is why I gave you option of last 3 number and 1, 2 up to 7, not up to 9. 8 and 9 are excluded because the catalog doesn't have. So this is the net practice session that you have a known galaxy you are learning, RGB optical radio analysis. But when in future you will get a tiny source and fuzzy contour, 2, 3 contours there. And you will struggle that there is no optical galaxy, doesn't look like a radio galaxy, nothing. And you will struggle unless you have certain amount of little bit of radio, this RGB net practice. Okay, discovery is not going to happen that you don't know what you have discovered. I usually say this question that when somebody says that I found a interesting leaf. So ask me the question. Somebody should be asking this way, that I have found an interesting leaf. It looks green. Then I will say, what is interesting about a leaf looking green? You should ask the question other way around, that I have seen all the leaf green, but this leaf exactly looks similar in structure, but color is red. Why is so? So you should be knowing the normal first, then spot the abnormal. Right? So this is our net practice. This is not yet the discovery started. This is just the training part of the discovery. Okay, anybody else?
Ananda, I want to add something here. Yeah. We were looking at NGC 1012. Yes. A little while away when we were discussing whether there is a ramp pressure stripping, the lopsided, the asymmetry.
You had a look at the object.
I just looked at the Google images. Huh. Yeah, I just looked at the Google images of the galaxy, and if you zoom out, take a zoomed out image, and see the surroundings, there's hardly any ramp pressure stripping evidence in that. So my guess is that it's probably a warped galaxy rather than ramp pressure stripping happening. But I mean, yeah, it has to be looked in detail.
You want to share that screen and talk a little? Or screen is gone, or you don't have that picture?
It's just a Google image. I can I can share the screen. 1 second. Yeah. So if it's visible, this is the Google image that I found.
No.
It's NGC. It's, I think, SDSS image.
Are you sharing?
Yeah, I've shared my screen. Is it not? Yeah. Is it not visible?
No.
It's okay. I'll do that again. Give me a second. Now is it visible?
No, ma'am.
Okay, there might be some connectivity issue then. It's you can just Google NGC 1012 and this is the SDSS image that I'm looking at. So there is an asymmetry there, but probably it looks to me more like a warp than ramp pressure stripping.
NGC 1012, right?
Yeah, I think, yeah, 1012.
It's a lenticular. It's
on Wikipedia. Yeah, it's a lenticular. It's on Wikipedia. I mean, I'm looking at the Wikipedia image, Wikipedia Commons image. There's also an image on the Sky ORG. It's a low resolution image. But there also I can
It has a
I
SDSS
can't make
picture.
out if there's any RAM pressure stripping happening. Yes.
And the SDSS picture is huge bulge and there's a dusty disc-like thing, I think. It is not a.
Yeah, exactly.
It is a lenticular. It is not a thin disc. Hubble type S0.
It's a lenticular galaxy.
Yeah.
I think I got disconnected.
Let me. No, I can hear you. Let me some other time see the H1 spectrum from this. If it is RAM pressure stripping or some kind of tidal effect, the gas will be more offset than the stars that we can see here.
Exactly. Yes.
The SDSS picture is so much of. Let me show my screen. Share screen.
Excuse me, sir. I have actually made 2 images on using TGSS and NVSS control under the comments of his post.
Okay, I will see that. But this, can you see my screen now?
Yes, sir. Yes, sir.
A huge bulge actually, and this part looks like simply dust and gas which is there, probably recently grabbed from the environment, and some amount of star formation which can be seen here. So this is unlikely due to the warp or due to RAM pressure stripping anything. Well, recently grabbed gas. Maybe tidal galaxy, tidal dwarfs nearby. We should see later. This radio, which is oriented this way, very suspicious whether it is really there or not.
And sir, and also the violet color diffraction spiked source, that might be I think it is quite a near one, may not be linked to the galaxy that is present in it.
True. But that is unlikely doing anything to the radio.
Exactly. So the DSS image that he had posted earlier, it had actually created that sort of a thing, like might be a case of.
Yeah, you posted Agni Preeti. Oh, you overlaid that. So it looks huge if it is real.
Sir, maximum value of TGSS there is just over 3 sigma. It's like 0.017.
Yes, sir.
So
this one survey has commented.
So for NVSS, it's pretty high than 3 sigma. But for TGSS,
how much?
For NVSS it is 0.023.
23 million ski.
Yeah, for TGSS it's 0.017. Like just over 3 sigma.
NVSS does not show the effect of anything in the environment. If it was RAM pressure, the one side could have been asymmetric. I should check in the.
That's what I guess by looking at the image.
Yeah. It's unlikely to do anything with RAM pressure. But we should look at in the literature first. Molecular gas or some kind of thing people would have H1 people would have observed. Unless the H1 spectrum is extremely asymmetric in the profile, I would doubt any RAM pressure effect or tidal effect. Okay. Let's move on. Any other question by anybody who is, look at the YouTube comments also. If somebody is asking something else, like what is the benefit of Rad at home? How can I join Rad at home, etc. Basic questions.
There were questions about how to use the tool, but I think it is from before you explained how to use the tool, sir.
Oh, Priya is also here. I see. Okay, anybody else?
Someone was asking how to join GMRT.
How to join GMRT? I wonder actually what does that mean? Is it joining GMRT Facebook group or join GMRT as a staff engineer, staff astronomer or technical assistant or
I
student?
think they probably mean the technical assistant or something.
I think every institute has their own way of selecting and recruiting people. You need to look at their website, apply for their job. And if it is something like a student looking for internship, write to their proper addresses. And if you are confused about joining GMRT for job or student, you can ask us also. We will give you proper email addresses whom to contact. And if it is, if you are confused about joining Red at Home and GMRT Facebook group, GMRT Facebook group is kind of a radio astronomy popularization group. It primarily spreads or shares news or contents regarding radio astronomy, including primarily Indian from GMRT, NCR, TFR authorities. And although I manage it for radio astronomy popularization, the RGB image analysis or discovery from that happens from Red at Home group. It's entirely different. But once you are through the Red at Home discovery thing and want to join the GMRT observation as a Red at Home discovering member, you need to observe first, you need to discover first, and then you will be able to observe with the GMRT later on. Okay, to become a co-investigator in GMRT proposals through Red at Home, you need to discover first. It's you can join Facebook group as easy as sending a friend request. Have your college or university affiliation expressed in your publicly in your profile. I will accept your membership. Then we'll discuss there. As you slowly grow in your RGB analysis, you will be promoted to the iAstronomer group, and then you will be part of discovery thing. Okay, I hope I have explained all the possibilities of how to join GMRT. Anything else?
Sir, someone is just writing to me in the chat box that I have sent the Facebook request. When can I join the group?
Okay, see, every Facebook request that I'm getting, I kind of go through a quick review that if you have locked your profile, I cannot know about you. I cannot accept you. If you have not put your profile picture, not put your proper formal looking name, if you don't express your college and university name there, I cannot accept you. And I simply decline or simply keep quiet for some time that you come and ask. A lot of people who email me or message me in Facebook, I give the standard reply that you update your profile with your college and university name, then send the request again. Because sometimes 30, 40 requests are pending. And then I have to keep declining everybody and message them that you update your profile, send the request again. Because this is a very minimum thing I'm going to check whether people are actually going to, because there are 5,600 members, there are 4,600 something I've forgotten, close to 5,000 at least, that people are sending advertisement of all kind of star party they are having, conferences they are having, webinars they are having. And I don't even care your star party there, simply because we are focusing on training RGB image analysis of galaxies, radio data analysis of taken from GMRT, nothing else. I don't talk about star cluster there. I don't talk about stellar astronomy there because we are focused. It's a research collaboratory. Okay, so there is no offend, there is no insult to anybody doing any other kind of astronomy, but we are focused. Sorry, we cannot compromise on this nature that we are from all places, nationwide Inter-University Citizen Science Collaboratory. You are free to join. Perform, you will grow. And don't expect me to answer everything. There are all the Red at Home team that you saw here describing, they are proven in this video that they are efficient. They can comment you, they can guide you. They have learned what you are willing to learn. Because several research institutes IIT, ISER, IOP, HRA, they have given free food, stay, everything to all these people for 7 days. They have taken the responsibility of training you in the group by posting comments. They also don't like to be in the Facebook and forget their studies, right? So other than Facebook, there is no option that we can do this. There is no option that who will give me the space, who will give me the computing, who will give me all this software support. So Facebook is the option. Facebook is a compulsion. Facebook is a majburi for me. Right? So minimum requirement, express your university. I will make you enter the group, and there we will start learning basic part. Yeah, somebody was saying something. Yes.
Yeah, I want to add to this. If by chance anybody's request is not accepted, and you want you're a serious person to learn these stuff, I would suggest you that you send a message to Ananda sir explaining your interest or explaining that what you want to do. So once that part is done and you actually are interested in learning it, he will for sure accept your request. Don't think that he will not, but you need to be focused in the same direction as the group is oriented towards.
Yeah.
So just express your interest accordingly. Your request will be accepted.
So everybody has certain amount of constraint. I respect your passion because I was passionate. I used to run home to listen to talks and watch Shoemaker-Levy line colliding on Jupiter. How many of you have seen? Have you seen the videos?
Videos, yes, sir.
Yes, sir, the videos we have.
Yeah. Every day in the evening 9 o'clock news, in the black and white TV that we had those days, I will come down just during the news. At the end of the news, they will show this, or beginning of the news when it becomes hot topic. Bomb, it will black smoke like thing. This cell will be next day. You can notice that the size of the patch is growing. So it was a beautiful event happening for several days. So that passion, of course, I did not become a planetary astronomer, and I did not become an optical astronomer. I was also there, like Mamta said, we have seen sky from Kavalur Observatory. I have gone to Mount Abu Observatory also, but I got stuck with GMRT because one single fact: this will be the largest radio telescope in the world. So whatever you will be detecting, I was making a small optical telescope during my college days, high school days. But radio, nobody can beat. I did not show you the picture. If you want to see, I can show you now also that how big is the telescope. I hope my slide will show you. I think I have that slide. Just compared all the radio telescopes of the world. Here. This is all the radio telescopes of the world, right? From the SCA website. This is LOFAR and SCA. LOFAR is here, SCA is being built here. GMRT, the collecting area is proportional to this size that you see here. JVLA is here. That's what I was saying, 3 times bigger than that. Okay, so currently, which is fully functional until this car comes, at this frequency range, we are the best telescope. So whatever you will observe is going to see definitely something new. That's what we will do next. Looking at the FITS file, we'll definitely see something new. Only point is whether just a new radio point or there is some new interesting science that we can derive out of that. That makes it a paper, right? So,
sir, I think.
Yes.
Parakram is raising hand. Yes, Parakram, you can unmute yourself.
Good afternoon, sir.
Good afternoon.
Sir, I was just randomly looking at different, different regions, and I was looking at NGC 478.
Okay.
And sir, in the image, sir, it is a, well, according to Google, sir, it's a spiral galaxy.
No, show me the image.
Yes, sir. I'll upload it in the chat.
The skill is that you can analyze and make statement from those data, not what the Google says and what the Wikipedia says. We should be able to become a net giver, not net taker, right? We should be able
Yes,
to
sir.
create knowledge. Yeah, show that picture.
Yes, sir.
I'm stopping the share.
Yeah, Parakram, you can just share your screen rather than uploading anywhere.
Yes, sir. Yes.
Oh, sir, if possible, after Parakram, can I share the screen as well?
Yes, sir. So, as you can see, sir, the NGC 478 has some very weird contours.
Yes. Where is the contour here?
Sir, this area, like the specific region at the top.
Okay. What do you think is happening in the galaxy or something, whatever it is?
Sir, according to, since this contour, the ROR is like circular, so I'm guessing it's a spiral galaxy.
But do you see the spiral arms in this galaxy?
Not really, sir.
Then why are you saying this is a spiral galaxy?
Sir, maybe because of this.
Spiral galaxies would have spiral arms, no? You have seen so many spiral galaxy pictures today.
Yes, sir.
But
sir, actually, I was confused as well. So I googled it up, and NG478 is, according to it, a spiral galaxy. So I just thought about that and correlated it with that. So I thought it was a spiral galaxy.
Okay. So what next you want to question, or you have understood?
Sir, I just had a big doubt, like why is there's a weird concentration of contour lines in this area?
First, interpret the radio optical UV, the UV optical IR image.
Yes, sir.
First, interpret that. Say something about UV, optical, and IR. Then we'll go to radio. Radio is more complicated.
Okay,
go to
sir.
the top.
Sir, I can't really interpret anything much except that it's just it's a deformed spiral galaxy. It's not exactly forming those spirals properly, but other than that, I can't really make many statements.
Forget about it. It is a galaxy, or what kind of galaxy? Tell one sentence comparing UV, optical, IR. What does UV shows in a galaxy? What does IR has been showing all this afternoon in all the RGB images? Okay, fine. See, what does UV shows in a galaxy image?
Sir, UV shows the new stars.
Good. What does IR in this band shows?
Sir, so this is IR, sir.
Yes.
Sir, I think this is the IR one.
Which one is IR?
Sir, the red one.
Okay, correct. The right-hand side top picture with red pixels is displaying the infrared image in 22 micron. Correct?
Okay, sir.
Then, what that 22 micron shows?
Sir,
what 22 micron represents?
So just a second, sir.
See, it is very simple. The moment you take an optical picture of your body, skin shows. The moment you take an infrared picture of your body, the blood veins will show. The moment you take an X-ray picture of your bone will show up. Very similar analogy I have said. What kind of emission, what component of the galaxy shows up prominently in 22 micron? What component of the galaxy shows up prominently in ultraviolet image?
Sir.
Okay. Anybody?
Hydrogen, sir?
No. You are from the Amateur Astronomy Club team, isn't it?
Yes, sir.
Okay. So some of you, any other of your member I want you to discuss this part. What different band is showing in IOU RGB image? Let me take this picture as your representative picture.
Sir, I think it would be in the low, if I'm not wrong, it would be in the low low infrared spectrum that it would be finding the image in, if I'm not wrong.
Yes, this low infrared spectrum, but what component of the galaxy shows up?
No, in IR.
Sir?
No radioatom member.
Sir, if I may answer.
Yes.
Sir, the infrared part is usually from the low temperature gas or dust.
Okay. So yes, correct. Not say those words, but say something more. Low temperature gas.
Yes.
Something more.
Something more in that. Okay. IR is low temperature, so gas.
I did not use the word gas.
Sir, if it's low temperature gas, then it would be either a very small star or a star that is probably dying.
I did not say either. I have been saying that the component of the galaxy, the interstellar medium, the gaseous, dusty PAH, polycyclic aromatic hydrocarbon, that component, when it is absorbing the stellar light, O and B type stars mostly, they are getting heated up, although they are 100 degree, 200 degree. If those radiation were not there, they would not have been seen in 22 and 12 micron either. For example, so-called dark clouds, Bok globules, if you go and try to make an image, they will not be visible at 22 micron, 12 micron or 8 micron even Spitzer, because they are even cooler than the 100 Kelvin. There will be 20 degree Kelvin or so. So the component which is there around 100, 200 degree Kelvin, they will be picking up like a black body, and the peak of the spectrum comes in 12 micron, 22 micron. So the red that is shown here is where the dust and PAH is. The UV is seen or not is a different question. UV is seen here from the surface, and deep inside that tube-like thing, pipe-like thing that you see here, ring-like thing that you see here, that is star formation is happening there, and dust and pH is signing up in 12 and 22 micron image. From the optical, you can see on the left that there is a peak there on the right hand side that most of the old stars are. My power has failed. Am I audible?
Yes, sir. Yes, sir.
Okay.
Yes,
so,
sir.
Okay. Let me come to your radio contour. Okay. In the top, you see only a tiny bit of 25 arc second beam, 150 megahertz radio contour. Go down to your picture. Parakram. Go down.
Yes, sir. Yes, sir. Sir, so all I wanted to know, sir, was why is this a really weird concentration of...
I am coming. Just go down.
Yes,
I
sir.
have not forgotten your question.
Yes, sir.
Scroll down, please.
Scroll down.
Yes, sir. Sorry, sir.
So here in 45 arc second blurred radio picture at 1400 megahertz, you see the emission centered around the center of this ring roughly. So most of the radio emitting gas is there around there. There is nothing weird. Wherever the green emission is picking up, roughly the radio emission is picking up there. So this is coming from the star formation process of this weird ring or galaxy or distorted galaxy or bent galaxy, whatever. Okay, coming back to the radio on the left side. The same thing is not seen there. The peak is different location, and peak is not as big as this. Forget about the resolution part. Now the left hand side, there's a tiny contour at the top. It could simply be a supernova remnant, a H2 region, a background galaxy. It could be anything.
So, sir, is there any
We
way of
cannot
finding
say.
out?
Yes, of course. There are other ways of looking at 2 micron, 3 micron image. Look at that if there is a background galaxy there. If it is there in 150 megahertz with certain amount of say 20 millijansky or something, the peak, whether at 150 megahertz, at 20 millijansky, say, any other telescope has detected it. If it is not detected at same level, then how many sigma detection is it? So if it is real, that means that it may be an explosive event. It may be a supernova at some point of time. That one telescope detects it time, and today it is not be detected at the same sensitivity. And day before yesterday, before this particular TGS observation, it wasn't there in the sky. At the same sensitivity, you have to observe. Then you will say this is a kind of an explosion. Probably it happened. It has kind of a radio supernova remnant, radio supernova, radio bright supernova. Right. So this is called the transient field that compare various database in various time. Given sensitivity, you can say there is probably a supernova there that sometime it has happened. And today, if you observe, it may not be there. It has died down, probably the emission has lowered. So this is how you actually analyze. This is very likely an interacting system or a ring galaxy or something. We need to look at a better image. Better than DSS image, SDSS image can be figured out. And there are many other data. DSS I am using simply because it is all sky. Okay. After, are you done? Is it okay? Done? Hello? I can't listen you. Hello?
Yes, sir. So probably he's having some net issues.
Yes, yes.
Parakaram.
Somebody else was saying something. Go ahead.
Sir, I think that was all the questions.
Okay, fine. Anybody else has anything to say?
Sir, actually referring to NGC 1102, like the one which you showed by Varun Dev. So
Yes.
like I checked on the literature survey, so it showed about the hydrogen line, like, and also like from images, we can say that because the contour is like highly bright in the NVSS, whereas it isn't that much well emission from that region in TGSS. So like,
What
can
the
we, yeah,
publication says? H alpha line or H1 line?
so H1, neutral hydrogen.
Okay. Do you see the profile there?
So actually I checked it on NED database in the classification section. So there were near about 7 to 8 references stating about the neutral hydrogen.
Fine, we'll see that profile and then come. Okay. If you have the profile asymmetric, then tell me. You have to look into the PDF file of that published papers. My power has failed again. So anything else? Mamta, do you want to say something? We will close the live streaming.
Yeah, I think we can wind up this session and we can close the live streaming. But is the link for Google Classrooms for the interaction with the e-astronomers put up on that
I have
live
not put
live board?
in the Read at Home live Google Doc. I'll be putting something now. Okay, because I have been speaking, I have not copy pasted anything yet. So
Yeah. I agree.
So say by 1445, if in the Google Doc your name does not appear, consider that you are not selected. Wait for participation in the Facebook group and some next opportunity. Otherwise, I will be putting your name in the Google Doc. Okay, give me some few minutes. By 1445, I will be putting in the doc, and that document link is already there. redathomeindia.org/live. There is a Google Doc there, so you can check if your name appearing for the next fits file analysis session. Is that okay, Mamta?
Yeah. So Ananda, the live link. Yeah. The live link is shared to every participant just now in the chat also. So you guys can go to that live link after say 10 minutes and check if your name has been selected for one-to-one session. There you will find a link for Google Classroom, which you're supposed to join, and the astronomers will actually discuss with you one-on-one. And now I'll hand over to the moderators for the closing remarks. So Abhishek, you can take over.
Yes, ma'am. Ishita, is there?
Yes. So thank you so much, sir, for this amazing session. We learned a lot from you today, and thank you so much. So thank you, Mamta ma'am. So with this, we would like to just close the session. So I think
want to have a gallery photo at the end, whoever is there.
Yeah, we
yes,
took
sure,
a
sir.
photo after in the beginning, just before your talk, we have a gallery view photo taken earlier.
Okay, fine. No
Yeah, so
problem.
we'll share that photograph with you. And I would like to thank Dr. Ananda and Dr. Charanjeev on the behalf of our university and on behalf of the TAS Society and all the students. So thank you so much, guys, for a very nice session. We had a fruitful day and hope to continue this ahead also.
Sure. Thank you very much, Mamta and the Thapar Institute for hosting us. And it's an opportunity to connect to large number of people. I was excited because of so many people registered. And even if they could not join this meeting, I hope we'll inform them and they can join some other meeting some other time. Okay, thank you very much. We can close the live streaming. In next 10 minutes, I will be uploading the doc.
Yeah,
okay. Thank you so much, sir.
Yeah.
Thank
Bye,
you.
everyone.
Thank you for
Bye,
organizing.
everyone.
Thank you so much, sir.
Thank you, sir. Thank you, ma'am.
Welcome.
Thank you, sir. Thank you, ma'am.
Welcome. Ananda, sir. Ananda, are you there?
Yes, yes.
Yeah. Abhishek, can you stop the live on live